Welcome to day 3 of this course on Bayesian modeling, inference, prediction, and decision making. Maybe I'll begin by orienting you to the new things on the course webpage. We have new material toward the bottom. So under the 1st of February, there's a variety of new handouts. There was a copy of Lecture Notes Part 2B posted 2 weeks ago. I have had to make some improvements to it since then. So if you've already downloaded Lecture Notes Part 2B, you can toss that one away and get the latest one. Then we have a copy of Richard Cox's paper laying out his logical progression from principles to axioms to theorems about how probability should work from first principles. So after we finish today, we'll finish up the stuff in part 2 of the lecture notes that we were partly way through. We'll talk about integer-valued outcomes and Poisson modeling in part 2b, and then continuous outcomes Gaussian modeling in part 2c. Here is a set of 2 things that you might find interesting. I've mentioned already this guy, this economist, David Leonhardt, from the New York Times, who often writes interestingly about quantitative things. And one of the things he's writing about here is he's giving a New York Times summary of an article from the journal Nature, which is also in this handout. So what you have is a couple pages of Leonhardt talking about it, and then you have the actual article from Nature. And what the people did who wrote this article is they tried to find out whether top-level athletes actually behave in a Bayesian fashion in combining prior information with current data information and playing against their opponents. And they discovered that actually people's behavior at the neuromotor level in their brains is quite consistent with Bayesian information processing. So you might find that interesting to look at. Then I have a variety of backup notes of the handwritten and extra variety, like I've shown you before. And there will be potentially substantial redundancy in going through all 4 parts of this, but it's not a bad idea to go through them anyway because each one of them has some stuff that's not present in the other ones. And then I have a new problem set for you and a new set of solutions for you. Some people have been starting to mention that they've been working through some of the problems and saying things like, I don't know if I would have been able to figure that out without the solutions you kindly gave me. So that's good because problems should be challenging enough that you work on them for a while and then get a little help. And then this last thing is a placeholder to myself. I want to give you, those of you who want to do this stuff in R, to create your own versions of the problem solutions, I need to tell you a little bit about how to plot multiple functions on the same graph in R. So that's a placeholder for me to create a PDF for that for next time. We also have videos up and running for all of the parts of the previous 2 sessions. The parts don't correspond to the sessions that we have in here, but just to how far they could get until they ran out of space on that particular chunk of ones and zeros, so to speak. So the 11 January meeting breaks out into 4 parts and the 18 January into 2 parts. And in due course, after this one today, I'll post the video for the other ones as well. So if you missed some or all of any of the previous sessions, you should be able to recover from that to at least some extent here at the webpage. And we will get to some of this stuff from R today because we'll get to these 2 things as we go along. So that's the stuff that's new from last time. And a reminder of the schedule of the day. I put it on this flip chart here, which I hope will be at least more or less readable to everybody. And it's also on the whiteboard over there, perhaps not written large enough to be fully readable, but same as always, we're going to go for an hour. with 15-minute breaks in between, then an hour for lunch, and then an hour, an hour, an hour. So basically same structure as before. I was working out, by the way, the other day that when we finish this class, you will have absorbed the content of between 1.5 and 2 graduate courses on Bayesian statistics. So we are, in fact, covering quite a large amount of material. So returning to part 2 of the notes, just a reminder where we were since we were off for a week. Maybe I'll take a moment to remind everybody where we were. I was talking throughout about a case study in which I'm going to see the binary death or no death within 30 days of admission outcomes of about 400 patients who were all admitted with a primary diagnosis of heart attack at one particular hospital in the Santa Cruz area, the Dominican Hospital, DH for short, over a particular 4-year time window that is of interest to me, starting in the beginning of 2006 and going through the end of 2009. And we examined 2 approaches to drawing inference, in other words, reasoning outward from those 400 patients to a larger universe of other patients who are similar to them in all relevant respects. And the main thing of interest, if you don't have any predictor information, which in this case study we did not, would be to focus on what people call the underlying death rate in that population, that larger universe that we're trying to learn about. And so that's the process of statistical inference. Later today I'll talk a little bit about prediction in this model as well. And we saw that there were a number of different ways to try to move forward. I showed you the frequentist approach by writing down a Bernoulli sampling model and then trying to use maximum likelihood to learn about the parameter theta in that model. And so we wrote out the likelihood function and plotted it, and we noticed it reached a maximum at the sample mean y bar, which was 18% mortality. And that's how Mr. Fisher, who popularized the likelihood idea, it was actually first invented by Laplace in the late 1700s, but 150 years later, Fisher wrote about it carefully and gave it a sexy name, and so we often associate the idea of likelihood and maximum likelihood with Fisher's name. He said, you're not allowed to think of that thing on the right here as a density in theta because that would make you a Bayesian. And you remember he tried hard not to work from the Bayesian point of view because he was seduced by the dreaded John Venn, who had talked him into believing that prior distributions were silly because they never have a relative frequency interpretation, or almost never have a relative frequency interpretation, when in fact that's just a weakness on John Venn's part in not understanding that there are other ways to think about probability. And when you regard probability as an expression of your information about something, then of course prior distributions are a very natural thing, and it's easy to think about them in real problems. Anyway, so there's Fisher saying, I would rather you think of that as a function, just a function of theta. And he says, trust me, finding the maximum of that function as a function of the data values will provide you with a good estimate of theta. That's the maximum likelihood idea. And we also saw that the logarithm of the likelihood function was important to look at, if only because the numbers involved in the likelihood function with large sample sizes tend to be very small, and so to produce better numerical stability, looking at the logarithm of the likelihood function is an important thing to do. And here we see that the log likelihood function in this problem is roughly quadratic around its maximum, and that matches the observation on the previous page that the likelihood function itself, when thought of as a density in a Bayesian way, looks a lot like a normal curve. And so if you take the log of a normal curve, you're going to get a bowl-shaped down parabola. So that's just how the normal curve works. And we also looked at Fisher's logic on how to come up with an approximate give or take, a standard error for the maximum likelihood estimate. And it turned out to involve calculating minus the second derivative of the log likelihood function evaluated at the MLE. That was what we now call observed information. And then he found out that you can get a good large sample approximation to the repeated sampling variance of the MLE by simply taking the reciprocal of that number. So he has provided us with approximate machinery, which was perfect technology for the 1920s for learning about parameters. You start with the MLE, and you go roughly 2 standard errors either way, because following the logic of Mr. Neyman's confidence intervals and reasoning backwards from a probability statement that was purely frequentist into producing one that allows you to construct an interval based on the data. To get 95% of the frequentist probability in the middle of that distribution, you have to go roughly 2 standard errors either way. and you get the standard error by calculating the information and taking its reciprocal, and then taking the square root to get the standard error. So pretty nice large sample, by the way. He doesn't make any claims for how well it works in small samples, but pretty nice large sample technology, especially well suited to the 1920s when differentiation was relatively straightforward and integration, which is at the heart of the Bayesian story, was relatively difficult. And this formed the backbone of most inference work in the world from the mid-1920s probably through the middle 1970s. So his idea had a 50-year run, which is a pretty good thing in science when you come up with an idea that's good enough that no one can better it over a 50-year period. Then we began talking about the Bayesian approach, which is quite different, in which we, from the De Finetti point of view, the one that I was showing you here, in which we think about trying to predict the 400 ones and zeros that you're going to see before you've actually seen the 400 ones and zeros. And so that corresponds to, it's easy to write down in LaTeX symbols. It's your Bayesian, the me part, my Bayesian predictive distribution for how the data will come out, having not seen any data yet. It's easy to write that down in LaTeX symbols, but it actually, in our problem, it's a 400-dimensional probability distribution. And we humans have hard enough time thinking about 2- or 3-dimensional probability distributions. So at the beginning of De Finetti's approach, it looks like his program is doomed to failure because that's just going to be too hard to think about. But then he pointed out to us the important fact that if you don't have any covariate information, by which I mean predictor variables or features with which to distinguish one of these heart attack patients from another, then you're actually your predictive distribution has quite a strong property based upon ideas of symmetry. First of all, without any identifying information, your uncertainty about person number 92 is the same as your uncertainty about person number 192, and so on. So all of your marginal predictive distributions have to be the same under that state of uncertainty. And moreover, even more strongly, if someone unknown to you were to randomly permute the order in which you saw the data values, you'd have the same predictive distribution for your original data and also the permuted data, because you have no information on which to distinguish one person from another. So he called that property of your uncertainty about something exchangeability. And he was able to prove an amazing theorem, which we took a while understanding, which basically says at the end of the whole thing that, in effect, if you're prepared to extend your judgment of exchangeability from just the 400 ones and zeros you're going to see to a broader universe consisting of what you would get by continuing that process out into the indefinite future, and that in effect represents thinking of the data as like a sample from the population of the countably infinite sequence y1, y2, ... Then you can begin thinking about the long-run mean of the ones and zeros in that countable sequence and call that number theta. And your model then turns out to have a simple hierarchical character. If you knew what theta was, you get the same sampling distribution that the frequentists do. The yi given theta is I d Bernoulli theta. But now you have to think of theta as something unknown to you, which it is. And in the Bayesian story, you always express uncertainty by means of probability distributions. So theta is like a draw from a distribution. And this provides our opportunity for bringing in the prior information, the information external to the present data set. So we talked about the implications of this for a while. And we then made some calculations. I showed you what happens in a setting in which I'm going to quantify the prior information of someone like me before I saw the data who didn't know anything about the Dominican hospital. And so that suggests that whatever the 30-day mortality rate in the US is, namely I can find that out by looking on the web, 15%, I should center my prior at around 15% because I don't know anything to the contrary. And moreover, having lived in the Santa Cruz area for more than 10 years, I would be very surprised if the underlying death rate at the Dominican hospital was a lot smaller than 15% or a lot bigger than 15%. And I quantified that statement by saying I'm going to put 95% of my prior mass between 5% mortality and 30% mortality. And all of these things are subject to sensitivity analysis. I could change the 5 and the 30 and the 95 up and down in reasonable ways. And what turns out to happen in this case study is you always get the same posterior distribution, or more or less, just apart from a little bit of mumbling out in the second or third decimal place. Not much going on at all. I'd like to find a flexible family of densities on the unit interval that I can use to quantify that prior information. And we saw that the beta distributions turn out to work quite well. They can provide shapes ranging from uniform to a strange sort of bathtub shape to long left or right-hand tails, to things that look rather like normal curves except restricted to live on 0, 1. The one thing that the betas can't do is they can't produce a single member of the beta family cannot produce a multimodal distribution. But as I think we talked about a couple times ago, you could, if you had to have that kind of prior information, you could express that with a mixture of betas because that'll give you several different modes in the mixture. And the other thing that was cool about the beta was that we know the likelihood function looks like theta to a positive power times 1 minus theta to some other positive power in this problem. And that looks just exactly like the mathematical form of the beta distributions. And moreover, by Bayes' theorem, the posterior is the product of that prior times the likelihood. And even cooler, it turns out that quite specially, the product of any two such functions is another such function. That doesn't always happen with probability distributions, but it works with the beta. And so people say that the beta distribution is conjugate to the Bernoulli likelihood, and therefore also to the binomial likelihood, because the way you get a binomial is just add up a bunch of IID Bernoullis. And I'll show you that in a minute. So, and that makes the conjugate updating rule very simple. I solved to figure out which member of the beta family corresponded to that prior information I showed you and got a beta with parameters 4.5 and 25.5. And the updating rule looks like this. If your model on the left is that theta, the information about theta can be quantified by thinking of it as like a draw from a beta distribution with parameters alpha and beta, and then conditional on theta, the yi's are IID Bernoulli theta, then in the Bayes' theorem updating, the posterior distribution will be another member of the beta family, and there's quite a simple updating rule. Alpha updates to alpha plus s, and beta updates to beta plus n minus s, where s is just the sum of the ones and zeros. In other words, it counts how many people died in the data set. And so here's a plot of the prior and the likelihood and the posterior on the same graph. And you can see because the prior is relatively diffuse, has a relatively large prior standard deviation, it doesn't affect things very much. It moves the posterior a little bit toward the prior, which is always what happens in Bayes' theorem. It's a kind of a compromise between the two. And in fact, we saw that you could think of the prior as equivalent to a data set, and it turned out that the effective sample size of the data set was what you get by taking those numbers alpha and beta and adding them together. So it was as though the prior was like a data set that had 30 votes in it, and the likelihood is like a data set that has 400 votes in it, and then the posterior is a compromise between those two. In a voting sort of sense, you combine all the votes into one pot and see what you've got. And so no wonder the posterior is a little bit shifted backwards toward the prior, because that's the nature of the averaging process between the prior and the likelihood. Okay, and we found out also that another cool thing happens with conjugacy. The posterior mean can be written as a weighted average of the prior mean and the sample mean, weighted by the numbers of effective observations. And so alpha plus beta is the prior weight, and n, the sample size, is the data weight, and that provides a nice interpretation of the posterior mean as a weighted average of the two information sources. And I think we were somewhere around just at the end last time noticing that in this particular problem we get roughly the same answers as we do with the Bayesian approach as we do from the frequentist approach. So I went through the calculations and showed you that the 95% interval is quite similar and the point estimate is quite similar. And we saw that that was because, in fact, with a large amount of data and not very much prior information, you expect the likelihood analysis and the Bayes analysis to be similar to each other for that exact reason we saw a minute ago, because the likelihood density looks a lot like the posterior density. And Fisher, in his approximation, by maximizing the likelihood function, look, he's going to get a number that's a lot like the posterior mean. And moreover, his standard error from his Fisher information turns out to closely track posterior standard deviation when you don't have much prior information. So in effect, what Fisher did in 1925 was he created a way to do approximate Bayes. And it works under two conditions: when you have a lot of data and not much information external to the present data set. Then it's okay to do maximum likelihood calculations and pretend that you did a Bayesian calculation. Just use the numbers from the maximum likelihood stuff to inform approximate posterior distributions. And this justifies the relatively frequent practice of people reasoning in a frequentist way to come up with their numbers and then reinterpreting the resulting numbers in a Bayesian fashion. That turns out to be an okay thing to do under those two conditions: when the sample size is large, which will tend to make both the likelihood function and the posterior look a lot like normal curves, And secondly, when the amount of information about the thing of interest to you external to the data set is relatively small. Okay. Now, we were, I think, just about at this point here where we wanted to talk a little bit about prediction. And so the bottom of page 50 of part 2 of the notes gets on to the topic of Bernoulli prediction. And you will recall that we went through some logic 1 or 2 times ago to show that the predictive distribution had a particular form. It's a weighted average of the sampling distribution for the future data, weighted by the current posterior distribution based on the data you've seen so far. And now that we've computed a posterior, we can now go ahead and plug that in and see what happens. And so we know that if the posterior is also beta, but with new parameters, the posterior has parameters alpha star and beta star, where alpha star is just the prior alpha plus s, and the beta star is just the prior beta plus n minus s. Now, of course, if you're going to predict the next outcome in a Bernoulli sequence, it has to be Bernoulli, right? If it only has 1s and 0s as its possible values, we know already without doing any calculating that the predictive distribution has to be a member of the Bernoulli family. But the question is, Bernoulli with what success rate? And probably your intuition, if you thought about it for a minute, would indicate to you that it should be Bernoulli with success rate given by the posterior mean, the value we got from the posterior distribution. And when you do this nasty integral, it turns out to be something that involves integrating over the same beta kind of integral that we had in defining the normalizing constant in the beta family. When you're done, you get the following distribution. The predictive, this is equation 39, the predictive for the next observation has that very busy-looking expression. But it turns out that there's a lot of ratios of gamma functions in there. And it turns out that gamma of x plus 1 over gamma of x is just equal to x for any real number x. So quite a lot of simplification occurs. And when you substitute in lowercase yn plus 1 equals to 1, in other words, talking about what's the predictive probability that the next observation will be a 1 given the data we've seen so far, it reduces to exactly what your intuition says, namely the posterior mean, alpha star over alpha star plus beta star. So the point here is that I would expect, based on this data, both internal and external to the data set, that the next AMI patient who comes along to die within 30 days of admission with probability about 0.178. And that makes, I think, pretty good intuitive sense. Now, the binomial, we've actually understood for free, having gotten the story for Bernoulli sampling, we actually understand the story for binomial for free, because we saw that a sufficient statistic for theta in the Bernoulli model was the sum of the y's. And you remember what that means. A particular function of the data vector is a sufficient statistic for the parameter of interest if the likelihood function depends on the data vector only through that simpler function. So that means that if you buy into the model that yi given theta or iid Bernoulli theta, you don't really care whether you observe the entire data vector y1 through yn or its sum. And so what is the distribution of its sum? Well, it's just the binomial distribution with parameters n, how many 1s and 0s were added together, and theta, the success probability in the Bernoulli. And so that means that actually then we have already worked out a new updating, a conjugate updating rule for the binomial as well, because if we observe the binomial sum of the 1s and 0s, then it will have a probability mass function given by this expression here. And the n choose s part does not depend on theta, so it would just be absorbed into the constant. And look, we're right back to the same exact likelihood function we had a minute ago, as we must. So here's another conjugate updating rule in simple Bayesian modeling. If your data set just consists of a single draw from capital S, we could call it, from a binomial distribution, then the conjugate prior is the same beta distribution we had a minute ago for working with the individual 1s and 0s, and the updating rule has that same rather simple form. If your model is that S given theta is a single draw from a binomial distribution with parameters n and theta, and your uncertainty about theta external to that data set is captured by thinking of it as like a draw from a beta distribution with parameters alpha and beta, then the posterior is also beta. And the exact same updating works as when we were just looking at the 1s and 0s. Alpha updates to alpha plus s, and beta updates to beta plus n minus s. Now, I would like to make a couple important general points before going on to new topics. First one is to pay attention to the sequential nature of Bayesian learning. So we know in science the way things work is that When you get up in the morning, if you've been paying attention, what you know is all the stuff about something of interest to you is all the stuff that you learned prior to that moment in time. And now you live through this day, and new information comes in that helps you understand better the thing you're interested in. How should you combine that new information? Well, the answer is Bayes' theorem. And you should use the information that you got up with in the morning as your prior, and then the new information comes in through your likelihood function, and that gives rise to a posterior distribution in the evening. Now, the next morning, I get up again, and I want to have a new prior distribution for today, which is one day later than previously. What should I use intuitively for my new prior this morning? The posterior from yesterday. And so that turns out to be exactly correct in the Bayesian story, and you can parse it out and see. So suppose you and I are observing a data stream y1 through yn to learn about a parameter theta, and we have no reason throughout this observation process to change the sampling distribution part of our model, otherwise known as the likelihood function. So you and I agree on the likelihood function. But now we both start with the same prior P1 of theta before any of the data arrive, but you and I adopt what appear to be different analytic strategies. You wait until the whole data set y1 through yn has been observed, and then you update our common prior directly to the posterior. Whereas I stop after seeing the first m observations, where m is some number less than n, and I intermediately, so to speak, update our common prior to an intermediate posterior distribution, which is p of theta given only y1 through ym. And then I go on from there, observing the rest of the data stream, and finally updating to a posterior on theta that takes account of the whole data set. So two different ways to analyze the data. One of us is doing it sequentially. The other one is waiting till the whole data set is in. Intuitively, should we get the same results? We have exactly the same prior. We have exactly the same likelihood function the whole time. I just chose to stop after a while and update, and then start up again and update again. Same information both in the prior and in the likelihood function. Therefore, we have to get the same answer. But only if I make sure that I do what you guys just told me, that the prior distribution for the second updating is the same as the posterior from the first block of data. And so, question, what should I use for my intermediate prior distribution? It has to be the posterior from what you've seen so far. And so the informal way people refer to this is to say that yesterday's posterior distribution is today's prior distribution. And then question two, if I use the posterior in answer one, do you and I get the same answer for the posterior in the end? And the answer is yes. And you can check this. It's not hard to check. So from that point of view, the Bayesian way of looking at the world provides a very natural framework in which to incorporate new information in a temporally sequential fashion. And since that humans don't know how to live backwards in time, we only get to live forwards in time, then why not use this tool? Every time new information comes in, you combine it, you construct the likelihood function for it, and you combine it with your prior information, which was earlier your posterior, based on what you knew before, and iterate Bayes' theorem again. And you can stop any number of times in the middle of that process, and as chain along, as long as yesterday's posterior is today's prior, you keep chaining like that, you'll get the same thing as somebody who waited for the whole data stream. Now, a second general point refers to how conjugate analysis works. It seems like a good thing, right? I've shown you it has a number of nice features. The math is straightforward in conjugate analysis. And that's really the point of conjugate analysis. It was chosen to be such that if you can find a prior that has the same mathematical form as the likelihood function, and the product of two such functions is another such function, then by Bayes' theorem, the posterior has to have the same form as the prior and the likelihood. And that means that if you've learned the mathematical properties of the prior distribution, then you've already learned the mathematical properties of the posterior also, because the posterior and the prior have to have the same form. So very nice, and Bayes was the first person to notice this. The only distribution he noticed it on was the one we're talking about now, the beta as a conjugate prior for the Bernoulli binomial likelihood. But he already knew about it in 1760. Okay, so that's great. It's relatively mathematically straightforward. Moreover, the posterior mean turns out to be a weighted average of the prior mean and the data mean. And thirdly, we've seen that the prior is nicely interpretable as an information source that's equivalent to a data set. And it's easy to read out what that data set looks like, and in particular what the prior sample size is. And then you can compare the prior sample size with the data sample size and look and see if that seems to be about the right amount of prior information to be coming in. Those are all great advantages. But I don't mean to imply, by having pointed out the conjugate story for you so far, that the conjugate story is the only possible one for prior distributions. It was actually originally adopted just for mathematical convenience. And then people noticed later on it had those other nice two properties about combining information. Whenever anybody tries to sell you something, it's pretty natural that you should wonder if you're going to behave under the new paradigm offered to you by the person who's selling it to you. This person will pay a lot of attention and will draw your attention to what's gained by taking the new paradigm on board. But that person who is an advocate for the new paradigm may not always remind you of what is lost at the same time, right? So whenever, here's me, let's say, I'm not really doing this, but here's me trying to sell you on the idea of conjugate priors, and I just showed you what's gained. We have these lovely things at the bottom of this page 55 about weighted averages and prior sample sizes and so on. But it's natural whenever anybody offers you something new to ask not only what's gained, but also what's lost. And it turns out that the main loss is that in their simplest form, they're not flexible enough to express all possible forms of prior information. And I gave you an example of that already. If for some reason you had a prior information source that was bimodal, that's impossible to achieve in the beta family. But if it were really bimodal, then as I mentioned before, why not just set things up as a mixture of 2 betas or a mixture of 3 betas or however many is necessary to get the number of modes that you have in mind. And so that suggests that the conjugate priors, even if they are not rich enough in and of themselves to encompass all prior distributions, they might be thought of as serving as building blocks. And it suggests the idea to wonder, if I were to take mixtures of conjugate priors in a particular problem, am I able to get as close as you would like to any possible prior distribution? And that answer turns out to be yes. Percy Diaconis and Don Ilvasaker proved a theorem a few decades ago that shows the following thing. I'm about to tell you what the exponential family is. It's a particular way of writing down sampling distributions that makes them follow from a common structure. So given a particular likelihood that's a member of the exponential family, their theorem shows that any prior distribution, no matter what, how strange it is, can be expressed as a mixture of priors that are conjugate to that likelihood. So that's a very nice sense in which the conjugate priors act like building blocks. If you like to think of a linear algebra sort of sense, the conjugate priors act like basis functions in a space where you're trying to span all possibilities by taking weighted sums of the different things. For example, in the heart attack case study, the model could be if you knew what some variable that keeps track of which mixing group you're from, capital J, theta given J would be beta with different parameters, alpha J and beta J, and then J would be a draw from a prior distribution on how many modes there are and how much probability is in those modes. So that's a way to generalize the previous model to account for the possibility of multimodal prior. And then the third level, of course, would be the same Bernoulli we had before. This is completely general, but unfortunately it loses some of the advantages computationally. Closed form computations are no longer possible with this mixture prior. You would have to go into Markov chain Monte Carlo, which we're going to start talking about next time. Mm-hmm. It's a weighted average. What I mean by that is, for example, a mixture of 2 normal distributions would look like this. No, it's going to be an additive sort of thing. So let me try to find where I am on this screen. I'm at that awkward moment with my eyes where far vision is quite different from near vision. So I have to keep going back and forth between one set of glasses and another. Suppose you take P and you use that as a mixing weight times the normal distribution with mean mu1 and variance sigma 1 squared. And you add to that 1 minus P times a normal distribution with mean mu2 and sigma 2 squared. That would be a mixture of 2 normals. And obviously you can extend that to an arbitrary finite number in the obvious way. And this particular model now has 5 parameters. The normal on its own with one mixture component only has 2, the mean and the variance, but the mixture has 5 parameters. And you can see that the number of parameters grows fairly quickly as you continue to add mixture components. But this turns out to be quite a nice family to learn about and be able to work with, because actually it turns out that all possible sampling distributions for data that lives continuously on the real line are expressible as mixtures of normals. You have to be prepared to allow for a very big number of mixture components, and you have to be prepared to allow for some of the mixtures to have very small variance, to act almost like point masses. But if you're given that freedom, then any sampling distribution in the world can be expressed arbitrarily closely by a mixture of normals with enough mixture components. In the math jargon, people say that the normal distributions in a mixing sense like this are dense in the space of all possible sampling distributions. You can get as close as you want by having enough mixture components. Okay.
So Bayesian's, I guess I would call it an additive update model. I don't know if it's the right thing or not, so I take what I've learned, I use for prior, I learned something, I put that in the posterior, and every time I'm doing a weighted average.
Well, let's see. Bayes' theorem itself talks about multiplying the two when thought of as densities and then renormalizing. And if you take the log of both sides of Bayes' theorem, you get log posterior equals log prior plus log likelihood. And so you could think of information accumulating additively on the log scale. That's true.
So, my vague understanding is that it uses exponential getting. So maybe it's on the routing. Somewhere at this level, it's not. When I get more information, I exponentially pay my old information.
That is probably, if we analyzed it carefully. So what he was asking for the benefit of posterity, not having a microphone, is he was thinking about the way TCP works as a information processing protocol for routers, for example.
Yeah, it's the size of the window that I have to.
Mm-hmm. And he's remembering that the TCP story has an exponential decay built into it. The way we would think about that from an information processing point of view is that it is an approximation to what you really should be doing, because you really should always be carrying along all the data you've had before if you're trying to update sequentially. But that becomes quite complicated sometimes, and so you exponential decay and hoping that the stuff that was out there before the exponential decayed quite a lot is not important to predicting the next thing that's coming along, for example. So I would regard that as, if we were to do the details, I would hope it would be an approximate Bayes thing to do. The other thing to say as a general matter, now that we've talked about both maximum likelihood and the Bayesian story, is that the maximum likelihood story definitely has some strengths. And I haven't shown you here today this fact, but it turns out that Fisher's approach extends quite readily to situations where the unknown is not just a single number, but it's a vector. So if theta is a vector of length k, of dimension k, for instance, then it turns out that the repeated sampling distribution of the MLE when it's a vector, not just a single number, is still a Gaussian, but it's now a multivariate normal distribution of dimension k, when k is how long the theta vector is, centered at the truth, and given by the analog of information, observed information, when you have a matrix, a matrix expressing your uncertainty about a vector. So this thing has to play the role. We remember how uncertainty works for vectors. This has to play the role of the covariance matrix of the multivariate normal distribution. And Fisher showed not only that the idea we had before, minus the second derivative of the log likelihood function evaluated at the MLE, that works for one unknown, but he showed how to generalize it to multiple unknowns. And the basic idea is, if you're starting to think that the variability information is contained in the matrix you get by taking second partials of the log likelihood function, then why not collect them all together into a k by k matrix, take the log likelihood function and imagine taking its partial with respect to two things at once, always maybe theta 1, that gives you the second partial with respect to theta 1, another entry, and it might be the partial with respect to theta 3 and theta 5, and so on. And that's, in math, that's called the Hessian of a function. It's the matrix of second partial derivatives of that function with respect to its arguments. And what Fisher was able to show is that this thing here, the analog of I hat in this expression here, is simply minus the Hessian. So minus the matrix of second partial derivatives of the log likelihood function evaluated at the MLE. And the analog of taking a reciprocal, which we saw before was the right thing to do in one dimension, turns out to be just to take the inverse of that matrix. So something very nice and tidy appears. We can use the same exact notation that we had before. It's just that the I hat is a matrix now, and the -1, instead of being a reciprocal, is now the inverse of the matrix. And theta hat MLE are now vectors, and the Gaussian in question is a k-dimensional Gaussian, not a one-dimensional. So Fisher was able to show that his technology works in large samples, not just for one parameter problems, but also for multi-parameter problems. And that really threw open the field of applying maximum likelihood to a very wide range of scientific problems. That's an important reason why it was the useful paradigm for 50 years or so. So maximum likelihood is a successful general approach to parametric inference when the sample size is large and little or no information external to the data set is available. And in this case, we'll find, just as we did in the heart attack case study, the maximum likelihood story and the Bayesian inferential story will tend to be similar to each other. But what happens to maximum likelihood when the sample size isn't large? And also what happens to maximum likelihood when you do have a substantial amount of information external to the present data set? Well, evidently, those might be situations where Fisher's approach doesn't work so well. So here are some disadvantages of maximum likelihood, and they all arise from the understanding that what Fisher was really trying to do, although he would not have admitted this out loud very much, is he was trying to create an approximate Bayes analysis. Because we already know we have theorems that shows that Bayes' theorem is an optimal information processing tool, although he didn't know that for sure when he was doing his statistical work. Those theorems were proved in the 1980s. But if you start with the premise that the Bayesian story is an optimal information processing story, then anything else you're going to do to be any good has to be approximate Bayes, because the Bayes way is the right way to do information processing. And so, in effect, what Fisher was doing with maximum likelihood was he was inventing a way to do approximate Bayes, even in problems of dimension bigger than 1, that involved only differentiating first and second partial derivatives of the log likelihood function, which is a really easy thing to do. Even when the maximum likelihood equations can't be solved in closed form, we saw in that problem it was easy to solve the one maximum likelihood equation to get the estimate. When you have more than one parameter, you often are in a situation where trying to solve the, let's say, 3 equations and 3 unknowns for a vector of 3 components, there is no closed form solution. He showed how to, naturally enough, construct an iterative scheme for finding the maximum likelihood estimates numerically through iteration. Newton-Raphson sort of scheme, if you've ever looked at trying to maximize functions numerically. And he showed how information from that search could help to provide you with a good approximation to the Hessian that you need, and therefore to construct your standard error. So excellent technology for the 1920s because it served as approximate Bayes, but only in 2 situations, in situations where 2 things are true: large N and not much information that's relevant to the problem external to the present data set. So it turns out with small sample sizes, when the likelihood function tends to be highly skewed, we saw here in this problem with 400 observations, the likelihood function looked a lot like a Gaussian, but oftentimes in small samples, the likelihood function can be skewed, can have a quite sharp long right-hand tail, for example. Then maximizing over that distribution is not necessarily the best technology. And I think I showed you this little sketch before, but let me show it again. We're going to see later on when we talk about hierarchical models that we're going to have Posterior distributions for variances in a model, and that's going to be approximately the same as the marginal likelihood for that particular parameter. And there are easily data sets in which this distribution looks like that. It has a maximum at 0 and then tails off in a reverse J shape from there. So if that really were your likelihood function, Fisher's methodology is going to find the maximum at 0 and is going to say that sigma hat squared MLE in this model is 0. Now, if you gave this data set to people in your statistics 1 class and asked them to summarize it and reminded them that every single value in the data set is bigger than 0, most people would agree that 0 is a rather poor summary of that data set when every single number in the data set is bigger than 0. So what the Bayesian story does instead is it draws your attention to a place like the Pasteur mean for sigma squared given the data and the background information. And that's going to be a value that will do a better job of propagating your uncertainty. Because if you come away from this part of the analysis pretending that that variance is 0, then you're underestimating how much uncertainty you really have about other things in the model by taking the variances that depend upon this quantity here and setting them to 0. And so even from a frequentist point of view, if you're trying to build interval estimates for things you care about, what will happen when you do this maximization here instead of integrating over that likelihood function is that you will end up understating how much uncertainty you have, because you'll be taking things that should be positive and setting them to 0 without meaning to do so. And so it's actually possible to show, and I'll give you examples of this several weeks from now, that Bayesian analysis of hierarchical models can have dramatically better frequentist properties than frequentist analyses of hierarchical models, because they do a better job of summarizing the information in settings where the likelihood function is badly skewed. Now, there's all sorts of SAS procs, for example, out there that will do some kind of analysis on the sort of hierarchical models that I'm talking about here and that I'll have more to say on in a few weeks. But those SAS procs never draw you a picture like this to show you that you're in a world where the maximum likelihood story might not work very well. They just give you numbers, and there might be some small print somewhere in the manual that says, this is a large sample analysis. And it doesn't even say, this is a large sample analysis, you are responsible for figuring out if your sample size is big enough for it to work. It just says, this is a large sample analysis. And people have been getting out some answers that aren't very good as a result from pretending that it's okay to maximize a function whose maximum is far from any other sensible summary of its center. Why doesn't this happen when n is large? Well, when n is large, we know that the likelihood function for some parameter theta is probably going to look a lot like the normal curve. Fisher says to maximize. The Bayesian story says to take the Pasteur mean, given the data and the background information. And if it's normal, they coincide, right? That's how the normal curve works. So his derivative technology, which was useful for the time that it was invented, does not involve this integration that would be necessary to work out where the mean is. His derivative technology works great for things that look normal, because we know with the normal curve the maximum and the mean are the same. But it can work rather badly for settings where your marginal likelihood function for a given parameter is far from normal. Another advantage of the Bayesian approach, or put it another way, another disadvantage of the frequentist approach, is that it encourages thinking of each data set in isolation. And I gave you an example of that last time. I'm pretty sure we talked about that Scottish study in the Grampian Mountains. Do you remember this? Also, it was an article from that guy David Leonhardt in the New York Times, where people did a single study of a particular new clot-busting drug, and they published a paper in the British Medical Journal saying that it was going to reduce mortality by 50%. They didn't bother to think of science as a cumulative process and try to fit their experiment into the march of knowledge about the idea of clot-busting drugs. And the Bayesian approach instead says, don't analyze your data as a one-off, which is what these Grampian people did, but instead think of this data set as part of a sequential progression of updating of information based on other studies. And when you do a proper Bayesian analysis, you get an answer that's much closer to what we now regard as the truth. So the maximum likelihood story is part of a paradigm for thinking about the world that encourages you to look at each data set one by one as a completely one-off, unrelated to other experiments that in fact are like it, and unrelated to other experiments that you have seen before. And so that's not a very good way to process information from a scientific point of view. And the third thing is that prediction of observables, which we're going to see as we go along in this course, is absolutely crucial to figuring out whether your model is any good, and is very easy to do from the Bayesian point of view. It's actually harder to do from frequentist point of view than you would like. Basically, I'm going to make a pitch later on to you in favor of the following common sense idea. Good models make good predictions of things you can see in the world. Bad models make bad predictions of things you can see in the world. That's one important way to tell whether your model is good or bad. So if you buy into that idea, which is a pretty fundamental one in science, then you have to get into the business of making predictions of observables and comparing your prediction with what actually happened. And in the Bayesian approach, the prediction is going to take the form of a predictive distribution. And so you're going to find yourself comparing your predictive distribution for some observable with the actual value that it took on. And that means you need a little bit of technology to compare a distribution with a single value, a single point. And we'll talk about that later on. There's a method called log scoring that people have invented that works very nicely. Well, the likelihood approach makes it quite difficult to construct those predictive distributions. Fisher had no idea of how to construct predictive distributions because essentially he would have had to do something, he would have had to make some kind of move in his argument that was explicitly Bayesian to get out something that was like a Bayesian predictive distribution. Now, much later, Brad Efron at Stanford invented the bootstrap in the late 1970s. And in my view, the bootstrap is best regarded in two ways. One is as the final chapter in Fisher's program to try to make maximum likelihood work, even in small samples. So the bootstrap does a much better job in small samples. It's in effect, it resamples from the data as a way to improve on the performance of maximum likelihood in small samples. And secondly, the bootstrap, when you use it correctly, can often also serve as a good approach to approximate Bayes calculations in problems with very large data sets. And we're working on this at eBay now. The bootstrap can often provide a computationally much faster approximation to the Pasteur distribution you want than trying to do the very complicated integration that we'll be talking about using Markov chain Monte Carlo starting next time. So the bootstrap is something that everybody working today should have in their toolkit, and by the end of this course, if you haven't used it before, I'll be reminding you how it works and showing you some examples of how it can help to provide approximate Bayes solutions. So that's it for part 2 of the notes, and we're heading now to part 3. Before I go on, does anybody have any questions or comments, possibly arching nature, before we switch gears? Where we are right now is that we know how to analyze data vectors that have the following character: an arbitrarily long sequence of binary outcomes with no covariates. So we don't know much yet. Now we're going to go up the ladder and talk about what if your outcome variable lives on the non-negative integers, and that will lead us naturally to Poisson modeling. Then after that, we're going to go up the ladder farther and talk about what if your outcome lives continuously on the real line, and that's going to lead us to Gaussian modeling and generalizations of Gaussian modeling. And all of that is still a world where there aren't any predictor variables, where we're just looking at a stream of outcome values without any predictors. And then later on, when we start getting into hierarchical models, we'll be talking about situations where the data lives anywhere it wants and you have predictor variables as well. So that's where we are in the big picture. We know we don't even know how to run yet. We know how to kind of stumble. And by the time we get done with the Poisson and the Gaussian cases, we'll know how to walk, and then after that, we'll learn how to run. So what was your question or comment?
When you talk about the observers, one of them stopped halfway through.
Yes.
Is that a type of those that you both end up with the same answer?
Yes.
Is that as a result of this?
You could think of it that way. It's to use a jargon that people sometimes use, it's baked into the Bayesian cake. The Bayesian updating in which Pasteur equals prior times likelihood is a perfect way to mathematically manipulate information sources so that yesterday's Pasteur becomes today's prior in a new update, and you simply chain along with a series of products like that. In fact, it's just sort of imitating the way the product rule works in probability. The probability that propositions A and B and C are all true is computed by working out the probability of A times the probability of B given A times the probability of C given A and B. And Bayes' theorem is providing you each of the little steps of that product. So it just comes right out. Uh-huh. The prior and the likelihood, yes. So what Tony's asking is, what if you're in a situation where you're trying to discriminate between two theories, I guess, and you have these theories you formulate these theories external to the data set, and now the data arrives and you want to see which one of them seems to be better supported by the data. That would be one way to describe it. Well, the Bayesian paradigm says compute the posterior probability that attaches to theory 2 and the posterior probability that attaches to theory 1 and pick the theory that has the bigger posterior probability. And that comes out naturally in thinking about what I think we already called in a very simple situation Bayes factors as a way of writing Bayes' theorem in odds form. Posterior odds equals prior odds times Bayes factor. And so the posterior odds in favor of theory 2 are just given by the prior odds in favor of theory 2 times the Bayes factor for theory 2 over theory 1. And we'll have numerous examples later on of how to make such calculations. Okay, so here we are in the world now of no longer dichotomous outcomes, but we're going to try to enter the world of integer valued outcomes. So I'm now in what's called part 2b. And to distinguish it from the previous copy that you might have already downloaded, the name of it, if you can read up there at the top, goes part-2- B rather than lowercase b. So if you'd already downloaded the lowercase one, this one is the one you want to be working off of now. So my new case study involves trying to model and predict hospital length of stay for birth of premature babies. I used to work at the RAND Corporation on problems in health policy back in the late 1980s, and as a small part of a study that I worked on there, we obtained data on a random sample of n equals 14 women who came to a single hospital in Santa Monica in the year 1988 to give birth to babies who were arriving before the normal due date. And the implied population that we're about to draw inference to is right there in that sentence, namely all the women who came to that hospital in Santa Monica in that particular year, because all we have is a random sample of 14 of those women. And if you wanted to be adventurous, you could try to push that farther out to make it a bigger population, all the women who are similar to the ones that arrived at this particular hospital. So it might even generalize to some other hospitals and to some other years as well, but that would require more thought. Well, one integer valued outcome of interest was the length of hospital stay. That translates directly into how much the care for having the birth occur costs. And they actually coded the length of stay in such a way that women who didn't stay even a full day were coded with a 0. And so here's a preliminary look at the data in R. So there's the data vector, it turns out. And you can see that it ranges from 0 up to 6. And I've sorted it to get a sense of which values are more likely. You see most of the women in those days only stayed 1 day. As you probably know, there's a big push in healthcare relative to the way medicine was practiced, let's say 40 or 50 years ago, to get people out of the hospital a lot faster than they used to. My wife's father had a cataract operation back in the 1970s, and he was in the hospital. He was hospitalized for his cataract operation. He was in the hospital for 10 days, and it was a normal cataract operation. Whereas I went to Stanford and had a cataract operation. It was outpatient surgery. I came out of the operation 5 minutes into the recovery room. I opened my eyes and I could see for the first time in my life, because I'm very, very, very nearsighted with my original lenses in my eyes, and now they put in ones that make me close to good vision without any correction at all. And it took a matter of minutes. I was actually on the road home after maybe 2 hours after they operated on me or something like that. So this is an era where they were also this push to try to get the women in and out of the hospital quickly already began. And there's a little table of the data values with the frequency distribution. And here's a stem and leaf plot of the data values, which is a kind of histogram turned on its side. And you can see it sort of looks like a Poisson. The mean turns out to be about 2.1 days, and the standard deviation about 1.5 days. And I see we have time now for our first break. So I'll come back and start talking again at 10:15. So we have this data that looks Poisson. And you may recall that the Poisson has a particular form. Its sampling distribution probability mass function looks like this equation 1 here. So the chance of getting a particular value lowercase y sub I equals lambda to the y sub I e to the minus lambda over y sub I factorial. as long as the y sub i's are non-negative integers, and you have no chance of getting anything else from this model, and that's for some lambda greater than 0. So this is a parametric family of sampling distributions indexed by a one-dimensional parameter, namely lambda. If you have forgotten its properties, I can use a package like Maple to work out simple things like its mean and variance. So I tell Maple that lambda is, the symbol lambda, it represents a positive quantity on the real number line. And I define a function p, which is a mapping from y and lambda to that exact expression I just said. And Maple comes back and says, this is what I think you mean. And it turns out that I got it right. And so then Maple is able to do infinite sums in symbolic fashion. So all the things I'm about to show you now have no numeric character to them at all. This is symbolic math happening here. So I ask it to simplify the sum of p of y lambda as y runs from 0 to infinity. And it says the sum is 1. No matter what lambda it is, as long as lambda is a positive number, the sum is 1. So that's nice. It verifies that it is a proper probability mass function. And then I say, simplify, please, the sum of y times the p of y given lambda. That's what you'd compute to get the expected value, as you know. And it says that no matter what lambda is, that particular expected value is lambda. And then I say, well, all right, what about the variance? Simplify the sum of the expression y minus the mean squared times the density. That's our expression for the variance. And it says that the variance of the Poisson is also lambda. So a basic fact about the Poisson is that the mean and the variance are both equal to the same number. And people sometimes refer to that by talking about what is called the variance to mean ratio, or VTMR. And here in this data set, of course, in this model, the sampling model, the Poisson, IID Poisson model, the VTMR would be 1. That marks the Poisson distribution out as a very special distribution on the non-negative integers. Most of the time when you work with data like this, the variance is actually bigger than 1, sometimes very substantially bigger than 1. So the Poisson is a kind of a funny first model you might well write down and then have to abandon later on when it turns out that the variance is bigger than the mean and you have to do something a little fancier. Okay, so, and I can informally check whether the Poisson is a good fit. R has a function called dPois, which calculates the values of the probability mass function. So I say dPois of the integers from 0 to 7, and I'll use as my parameter the mean of the y's just as an initial good guess for lambda, because after all, the sample mean, since the mean of a Poisson is equal to the parameter, then maybe the sample mean should be a good guess for that parameter. And so R comes out right away with those particular heights of the Poisson histogram bars, so to speak. And then I do a little bit of math in which I ask it to print a little table in which the first column just tells me the values from 1 to, corresponds to the integers from 0 to 0, 1, 2, 3, 4, 5, 6. And then the last row corresponds to 7 and above. And then the second column in the table gives you the Poisson probabilities for 2.07 as its lambda. And the third column gives the empirical relative frequencies, what percentage of the data values really were 0 or 1 or 2. And now, informally, in a way, you want to stare at those two columns, columns 2 and 3, and see if they look kind of similar to each other. And I guess informally, the basic story would be that they do look kind of similar to each other. When column 2 is large, column 3 tends to be large. And when column 2 is small, column 3 tends to be small. And if we wanted to do something more than that, we'd have to come up with some more formal way to compare two vectors of probabilities. And we could talk about that later. We could do another informal check. Since the variance and mean are supposed to be the same in the Poisson, the sample variance should be close to the sample mean. And so I can take that previous sample standard deviation of about 1.5 and square it and get a number like 2.4. And it compares more or less with the sample mean of about 2.1. There's maybe a little bit of a hint of what people call extra Poisson variation, where the variance to mean ratio is a little bigger than 1. I guess we'd calculate 2.38 over 2.07. And we get a number like about 1.2, I guess. So there's a little hint of extra Poisson variability, but as your first model, you'd probably want to try fitting a Poisson to this data set. Now, something's quite different here from the Bernoulli case study, In the Bernoulli case study, we used De Finetti's theorem to get the sampling distribution. It turned out that there was one and only one logically internally consistent sampling distribution. If your uncertainty was exchangeable, then you got to go with an IID Bernoulli model and then put a prior on the unknown success rate. Here, we do notice that having not seen any data yet, I'll put it in the first person, I noticed that having not seen any data yet, my uncertainty about those lengths of stay values is exchangeable because I don't know anything about the women, which ones are older, which ones are younger, which ones have comorbidities like diabetes or high blood pressure or whatever. So I do have exchangeability, but previously we had a theorem that said with Bernoulli, with 1-0 outcomes, exchangeability implies a Bernoulli sampling distribution. That's the right thing to do. That does not turn out to be true anymore when the data values live on the non-negative integers. We don't always get one and only one sampling distribution. And that gives rise to the phenomenon that people call model uncertainty. And what they really generally mean by that is uncertainty about the correct sampling distribution for the data. And that's a topic that I'm going to take up later in the course. For the sake of getting practice with the Poisson, I'm going to pretend that somehow I knew that down from the sky on a stone tablet that these data are yi given lambda are conditionally IID Poisson with parameter lambda, and then let's see how we could draw inferences about lambda. But I want to point out that in making that suppose, that's a big suppose, right? All of this is going to be a theorem of the form, if the data really are Poisson, then this is what we should think about theta on the basis of these observations. But so that's a correct mathematical theorem, but then of course the burden is always on us to see whether the if part actually is true in the world, and that's where the model uncertainty comes in. And so how to deal with uncertainty in the sampling distribution is a fascinating and important topic which has received a lot of thought in the Bayesian community, and that will be an important part of our meeting probably somewhere around week 7 or so. We're going to be talking about that quite a lot. Looking back at the structure of De Finetti's theorem, you could hope that a reasonable model where things were IID, rather where things were exchangeable, would be to think that there's some parameter theta, and if you knew what theta was, the yi's would be IID from some particular parametric family indexed by theta, and then you put a prior on theta. And it turns out, of course, that is the form that the Poisson has. So I'm going to pretend, without knowing that this is true for sure, that I'm going to fit the model 3 here, which says if you knew what lambda was, the yi's given lambda would be IID draws from a Poisson distribution with that particular lambda, and that will determine the sampling distribution or likelihood part of the model. And then, of course, lambda is something not known to us, and we quantify our uncertainty about that by thinking of it as like a draw from a prior distribution. In fact, what I just did is a kind of cheating, didn't I? I looked at the data to see what histogram shape it had, and it looked sort of Poisson to me. And so I said, okay, I'm going to pretend it's Poisson. That's got to be using the data twice, because the first use of the data is to arrive at the Poisson sampling distribution, and the second use of the data is going to be to figure out what lambda is if the Poisson were correct. Whenever you see anybody using their data set twice, the something for nothing bell should ring in your head, because they're pretending they have more information than they actually have. A naive version of using the data twice would be to take your data set and make another copy of it and just put it at the bottom of the first data set and merge them together. Now when I'm done with that, can I just go ahead and draw inferences and see what happens? Well, what will happen obviously is I have twice as much data as before, and so I'll end up with the same point estimate for something, but the uncertainty band will be what? Wider or narrower than before? Got to be quite a bit narrower. In fact, narrower by a factor square root of 2, because I just repeated the data set. Anytime somebody uses the data twice, we all know that that's not right, and a price has to be paid for one or the other of those steps. Yes. So he said, why not extract some of the data and use that to hunt around for the model, and then use the rest of the data maybe to update based upon what you learned in the first part. That's going to be an example of cross-validation, and I'm going to talk later on about a Bayesian version of cross-validation that I find works quite well. A very natural idea. Yes? Empirical Bayes doesn't solve this problem. Empirical Bayes says, he asked about empirical Bayes. Empirical Bayes starts with a model that has exactly the same likelihood line as this one does. In other words, empirical Bayes pretends you somehow know already that things are Poisson, and then in a certain sense it uses the data to estimate the prior distribution. That's what empirical Bayes does. So empirical Bayes does not solve the model uncertainty problem at all because it conditions on the same likelihood function as you would with full Bayes, and it just does a little cheat in which it, in effect, estimates the prior from the data. That's another form of using the data twice, right? Because I use the data to inform the likelihood line in this little hierarchical model, and I use the same data to inform the prior. And so you should be suspicious that empirical Bayes can sometimes not propagate uncertainty widely enough. It could come up with answers that uncertainty bands that aren't as wide as they should be, and indeed that is the case. I regard empirical Bayes as an approximation to a full Bayes analysis, which can sometimes be rigged to be a decent approximation, but will in general underpropagate uncertainty because you've used the data twice. So people regard this sort of using the data twice as a failure to what in a paper I published a long time ago now, the title of my paper was Assessment and Propagation of Model Uncertainty. So how do you assess it? And then once you've found out how much you have, how do you pass that uncertainty through to uncertainty about the things you care about? And we'll look at some of the ideas in that paper later in this course. You'll note that this is not a problem that is unique to Bayesians. Frequentists employ the same kind of cheating in specifying the likelihood function. Everybody in statistics looks at the data and uses what they see to figure out the sampling distribution. And there, bada bing, there's your likelihood function. And now you go on pretending you always knew that was the right likelihood function. Everybody does this, not just Bayesians. I think there are two basic Bayesian ways out of this dilemma. One of them is a particular form of cross-validation that I'll show you later on. And another one is an approach called Bayesian non-parametric methods, and I'll tell you about them as well. But to get more practice with Bayesian calculations, I'm going to ignore the model uncertainty problem and just pretend that somehow we knew that the Poisson was a good choice. And now let's see how you would go about learning about lambda if somehow you knew that the data really were Poisson. Yes, please. Yeah. Well, let's agree again on what the idea of prior information is. It's supposed to be a summary of all the information you regard as well-founded and accurate external to the data set. That information could come from eliciting opinions from a subject matter expert. It could come from other data sets that you already know about that you regard as relevant to the particular data set you're about to get. It could come from a variety of sources, and people don't actually have different names for that. But empirical Bayes does in general refer to the idea of using the data to estimate the prior. It's a shortcut. Instead of having to specify the prior, you leave the prior specification to the data. And at some level, that people for a while thought that empirical Bayes analyses automatically had to be more, quote, objective than regular Bayesian analyses, because you were using the data both in the prior stage and the likelihood stage. But in fact, the whole purpose of the prior is to give you a chance to bring in information external to the data set. And empirical Bayes doesn't do that. It looks at the same data set twice to decide how to specify the prior and also how to specify the likelihood. So full Bayes takes advantage of whatever information is available external to the present data set. And if there isn't much information external to the present data set, then we have ways of quantifying that as well, and I'll start showing you that in this example. So the only way we know how to construct a prior so far is to try to find a conjugate prior. And so let me remind you now, thinking of the first case study as an example of this basic paradigm, let's remind ourselves of what the steps are in constructing a conjugate prior if one exists. So we're in a parametric model, and so what that means is, given the background information you have and some particular parameter theta, you're thinking of the yi's as conditionally IID from some sampling distribution that's indexed by theta. and then you place a prior distribution on theta. That's the basic structure of all the models we're going to look at for a while until we get more adventurous. So what are the steps in Bayesian conjugate analysis based on what you saw last time? Well, first of all, you build the joint sampling distribution for the observables. And because of the IID story here, that's going to be the product of those marginal sampling distributions. So let me, in fact, write that in here. This is on page 7 of the extra notes from today that are posted. It says, no, it's the part called Handwritten Notes for 1st of February, part 1. So this thing here is going to be equal to the product of the marginals, P of yi given theta and b, by independence and identical distribution. So you first build your sampling distribution, joint sampling distribution. Then in step 2, you think of that as a function of the parameter for fixed data values, and that converts it into the likelihood function. Step 3, you think of the likelihood function as a density in the parameter theta, and try to find another density, P of theta, such that the product of those two has the same mathematical form as the prior. And that, if you can find such a thing, will be the conjugate prior. And that will generally occur by having the prior and the likelihood in the following 2 steps. The prior and the likelihood have the same mathematical form. That's step 1. And step 2, the product of 2 such functions is another such function. So that's how we found the conjugate prior in the Bernoulli analysis. And then step 4 in this program, we then use Bayes' theorem to do conjugate updating and create predictive distributions for future data. So that's what we're going to try to do now in this slightly more complicated case study involving Poisson sampling distribution. So how does the likelihood function go? I'm supposed to take the product. I have an arbitrary positive constant c in front, as always with likelihood functions. I'm supposed to take the product of things that look like lambda to the yi times e to the minus lambda over yi factorial. And if you write that out, again, from today's handwritten notes, you're supposed to go lambda to the y1 e to the minus lambda over y1 factorial times the same kind of thing with y2 times dot, dot, dot down to the same kind of thing with yn. And some cool simplifications happen. You end up with lambda to the power of the sum of all the y's times e to the minus lambda n times, so e to the minus n lambda, and then over the product of the yi factorials. But you recall that anything that's not a function of theta in the likelihood function is just regarded as a constant because we're thinking of it now as a function of, lambda in this case for fixed y. And so the product of the yi factorials, which looks like a horrible thing to have to think about, actually just gets absorbed into the normalizing constant. I just throw it away and put it into the C. So the likelihood function in the Poisson model looks like any old positive constant you want times lambda to the s times e to the minus n lambda, where s is the sum of the y's. And so just as we saw was true in the Bernoulli model, the sum of the data values is a sufficient statistic. That's all you need to know about the data vector to be able to evaluate the likelihood function. As a general remark about sufficient statistics, I called it a sufficient statistic because you can't talk about the sufficient statistic in any model because there's lots of different sufficient statistics. The definition of a sufficient statistic is it's some function of the data vector that has the property that if all you know is that function, you can still evaluate the likelihood function. But by that definition, the entire data vector is itself sufficient, right? But that's not much help because the whole point that when Fisher invented sufficiency was to try to get dimensionality reduction in the data space down from n observations down to a small number of observations. When the parameter vectors of length 1 and sufficient statistic exists, you hope it will have length 1. There are some weird problems where there's only one parameter and yet the sufficient statistic has length 2, but they aren't problems that arise in real applied work. And of course, if the parameter vector has length 7, you hope you find a sufficient statistic with 7 components in it and things like that. So y is a sufficient statistic, but it's kind of a stupid sufficient statistic because you haven't achieved any dimensionality reduction in the data space. Here's another sufficient statistic. If the sample size is even, then just take the sum of the first half of the data values and next to that, the sum of the last half of the data values. it's certainly true that if I gave you those two numbers, you could work out the likelihood function, because what you would do with them is add them to each other and get the sum, and then go ahead and evaluate it from there. So this is also a sufficient statistic, but it's not as good as the previous one from a dimensionality reduction point of view, because it has dimension 2, and we know that actually the previous one only had dimension 1. And so Fisher also invented an idea that we won't explore too much, but he said that you could find what was called a minimal sufficient statistic, and that's simply a sufficient statistic that has the property that it's a function of all other sufficient statistics. That sort of involves the minimal possible reduction. And essentially all it means by that is that you can't get any lower than one dimension with one parameter, and so there you are. Even with that, the sum is not the only minimal sufficient statistic, because 3 times the sum is also sufficient, right? So even the idea of minimal sufficiency doesn't get you to a unique sufficient statistic. You can multiply that by 3 and add 7, and that'll also work as well. But you see where Fisher was headed with all of that. Okay, so back to the PDF. We now can see that the likelihood function looks like lambda to the s e to the minus n lambda. And the next step in the program was to say, thinking of that as a density in lambda, does that remind me of any distribution I've ever seen before? Lambda to a positive power times e to the minus a positive number times lambda. And if all you're used to is frequentist statistics, you will probably not be as aware of a whole bunch of standard distributions as you would otherwise be. The Bayesian toolkit requires you to know a lot more distributions than the frequentist one does. So this does turn out to be a distribution that arises often enough that it has a name. It's called the gamma distribution. If its conjugate prior exists, it must be such that the product has the same form. So it does turn out, if you take a density of the form lambda to some positive power times e to the minus some negative number times lambda, not only is there such a density, it's called the gamma distribution, but it's also true about those functions that the product of any two of them is another one. So once again, the 2 steps in finding a conjugate prior both work in this problem here with the gamma distribution. This is the general way, one of the 2 general ways to parameterize the gamma. Alpha, as we'll see in a minute, is referred to as the shape parameter, and has always chosen for alpha to be positive, and then you have to go a lambda to the alpha minus 1 to make the thing be a proper density function. And then beta turns out to be related to the scale of the distribution, and beta also has to be a positive number. Now I have to warn you, and I'll have an explicit warning about this later on when we start going into R. This is not the only way people write down the gamma distribution. Everybody always uses a symbol like alpha or A or whatever to stand for the shape parameter. But the scale parameter, sometimes instead of writing e to the minus beta lambda, people write things like e to the minus lambda over s, for example. So for them, 1 over s is what we're calling beta, and 1 over beta is what we're calling s. And since both of those things turn out to relate to scale, there isn't any reason that one of these 2 ways to write it down is automatically better than the other one. So you just have to know out there in the world that there are 2 different ways people write gamma distributions. And to make sure you don't get completely wrong answers from any software that uses the gamma distribution, you have to pay close attention to which parameterization it's using as far as the scale parameter is concerned. I'll have more about that later. So one of our handouts from last time was some pages from the Appendix A in the Gelman book, and many distributions are listed there, and the gamma distribution is one of them. Maple, as usual, can work out the normalizing constant, so I assume that lambda and alpha and beta are all positive things, and I define the unnormalized density and ask it to work out the integral of the unnormalized density. And right away it says it's beta to the minus alpha times gamma of alpha. And we already know what the gamma function is because we needed to understand that for working with the beta distribution. So the normalizing constant is 1 over that. And the proper definition of the gamma distribution, at least using the parameterization I'm using here, is beta to the alpha over gamma of alpha, lambda to the alpha minus 1, e to the minus beta lambda. Where alpha and beta are sometimes called hyperparameters because they're parameters of the prior distribution for the central parameter lambda, and they both have to be, whatever they are, they both have to be positive numbers. And Maple can be used to explore the behavior of this family as a function of its inputs. So here I define the normalized version of the density, and I ask Maple to plot a whole bunch, actually 1, 2, 3, 4 of the members of this family, where the beta parameter is always set equal to 1, and the alpha parameter varies from 1 to 2 to 3 to 6. So here's the result. And so you can see that whatever's going on here, yes, please? Mm-hmm. Uh-huh. So the tilde part is Maple's way of saying, I am going to tell you what the right answer is to your question under the assumptions that you told me to make. If you haven't told Maple to do any assuming, then these would just be symbols BETA, ALPHA with no tilde behind them. But Maple, if I had not assumed that alpha and beta were positive, it would have told me that this particular integral has no unique answer because it doesn't even work for negative values of alpha and beta, and it produces infinity for negative values. And so in order to keep it from telling me things that are stupid, I start at the beginning of this session, a few lines above, by telling it that from now on, until I tell you otherwise, you are to think of lambda as a positive number and alpha and beta also as positive numbers. And then under those conditions that alpha and beta are positive, when you integrate the function lambda to the alpha minus 1 e to the minus beta times lambda, you get the expression beta to the minus alpha times gamma of alpha. That's what this means. You could look that up in a table of integrals, or you could use the symbolic computing part of the MATLAB package, or you could use Mathematica or Maple. They're all going to give you the same answer as long as you assume that alpha and beta are positive. So look, here's 4 different members of the the gamma family, and to separate out the meaning of the 2 parameters alpha and beta, I have held the beta parameter at 1 and just let the alpha parameter change from 1 to 2 to 3 to 6. And in fact, it turns out that reading from left to right, that's what these curves are. The leftmost curve is alpha equals 1. The next one over, reading to the right, is 2. The next one is 3. The next one is 6. So what seems to be happening here? It looks as though alpha controls the basic shape of the distribution. When alpha is 1, it actually is a distribution you've seen before. What distribution is that falls off in that fashion and has the value, looks like it has the value 1 at 0? It's the exponential distribution. So the exponential is a special case of the gamma where alpha is equal to 1. And then as alpha grows larger, what does the distribution approach in shape? For larger values of alpha, the gamma distribution looks more and more like what? A normal curve, but constrained to live on the positive part of the real line. So there's another kind of central limit theorem thing happening. In the gamma family, as alpha gets bigger and bigger, you get something that looks more and more like a normal curve. You can see also that the skewness of the distribution decreases with alpha getting bigger. That's part of why we said it looks more normal. So alpha evidently controls the shape of the gamma family. And now I ask it to, and I'll just codify this for us. When alpha is 1, the gamma distributions have a special form that we all recognize as exponential distributions. So this is the special case. If lambda is a draw from an exponential distribution with parameter beta, then I'm parameterizing it in the form beta times e to the minus beta over lambda. Again, you might see somebody else write 1 over beta times e to the lambda over beta, and that would be the same distribution but parameterized with the reciprocal of the scale parameter. Now I'm going to hold I'm going to hold alpha at 2 and change the other parameter beta from 1 to 2 to 3 and see what happens. And so here's what you get. And you see that they all have the same basic shape, namely long right-hand tail, but they seem to differ in scale in such a way that as beta gets bigger, the standard deviation gets what? Bigger or smaller? Looks like it gets bigger. Oh, I have to tell you what's going on. So the leftmost curve is the beta equals 1, then beta equals 2, then beta equals 3. So beta seems to control the spread or scale of the distribution. And I'll hold back on that. I might have gotten that backwards. Let's look at the next 2 paragraphs. People have found it useful to make the following definition. Given a random quantity y, whose density p of y given sigma depends on a parameter sigma that's positive, if you can express the density you're thinking of in a particular special standardized form, namely 1 over sigma times f of y over sigma, where f is a function that does not depend either on y or on sigma, then people call sigma a scale parameter for that particular parametric family P. And so if you use that definition and let f of t be e to the minus t and take sigma equals 1 over beta, you can see that the gamma family can be expressed just like this. So actually 1 over beta is the scale parameter when I'm writing things in this direction. And so actually 1 over beta is the thing that controls the standard deviation. As beta gets big, 1 over beta gets small. And so basically, actually, these curves, I should have put it into the PDF. These curves are in the other order. The one that's closest to the origin has beta equals 3, then followed by beta equals 2, then followed by beta equals 1. Okay, so now we have some idea what the parameters mean. And Maple can also work out symbolically the mean and variance of this family. So I say, I define a new perfect, fully normalized version of the density with the proper normalizing constant. And I ask it to do a symbolic integration of p of lambda alpha and beta as lambda goes from 0 to infinity. And it says the answer is 1. And that will be true for any positive alpha and beta. Then I go ahead and multiply that density times lambda and to see what the mean is. And the mean comes out alpha over beta. And then I say lambda minus alpha over beta squared times the density to work out the variance. And that comes out alpha over beta squared. So if lambda is a draw from a gamma distribution with parameters alpha and beta, then the mean of that unknown thing is alpha over beta, and the variance is alpha over beta squared. And again, people who wrote things in the other parameterization would think that the mean was alpha times beta, and the variance was alpha times beta squared, but they're just using the reciprocal scale story that we are. So now we can do conjugate updating. It's going to be pretty easy. By Bayes' theorem, the posterior is equal to a normalizing constant times the prior times the likelihood. And each of those things has a normalizing constant in it, but they can all be drawn together into a single normalizing constant, C. And multiplying the two gives another member of that family. And the updating rule is simple. Again, look what happens. Alpha updates to alpha plus S, and beta updates to beta plus N. So the resulting distribution is the posterior is just the gamma distribution with parameters alpha plus S and beta plus N. And that's summarized here in this little thing at the top of page 11. If your model for your sampling model for the data is that if you knew what lambda was, the yi's were I, d Poisson lambda, as I ran from 1 to n. And if you found it possible to quantify your information about lambda external to the data set by means of a member of the gamma family, and we haven't yet said what the alpha and beta are, then your posterior distribution would be another member of the gamma family, and it would have posterior parameters alpha star and beta star, where the updating rule is that alpha updates to alpha plus S, and beta updates to beta plus N, where S is the sum of the y's and is recognized as a sufficient statistic. It's actually even a minimal sufficient statistic for lambda in this model. So now let's try that weighted average idea and see if it works again. The posterior mean of lambda is equal to alpha star over beta star, which is alpha plus S over beta plus N. The prior mean is alpha over beta. The data mean is y bar, which is S over N. And if you write it out and stare at it, it actually does work. The posterior mean is a weighted average of the prior mean alpha over beta, in which, interestingly, the prior gets beta votes, and the other part is the sample mean S over N, in which the data gets N votes. And so right away, just from this expression 10, we can tell what the prior sample size is in this model. It's beta, because in this weighted average here, the data is getting N votes, and the thing that corresponds to N over there in the prior is beta. Therefore, beta is the prior sample size. And that makes sense because 1 over beta is a scale parameter. So as beta gets big, 1 over beta gets small, and that makes good sense. And the prior acts like a data set, in effect consisting of beta observations having mean alpha over beta. We can't say what the numbers are. In the Bernoulli case, we could say they had to be 1s and 0s. In this case, they just have to be non-negative integers, and there's beta of them in that data set, and the mean is alpha over beta. That's about all we can say about that data set. So suppose in this particular case study that before the current data set is scheduled to arrive, I know relatively little about the mean length of hospital stay of women giving birth to premature babies at this particular hospital in that particular year. Then I would want to put down a prior that was relatively diffuse. Close to flat are the kind of words I've been using so far here. Some people say I want to find a non-informative prior, but as I've told you before, I think that's not a very good terminology because every choice of a prior distribution conveys one sort of information set or another. So it's not true that anything is non-informative. It's just different information bases. But I want the prior to be flat. And so you can tell from this prior sample size what I want. If the prior sample size is beta, and I want there to be relatively little prior information, then what should I do with those parameters alpha and beta to make that happen? Make beta be small, right? And so that prior sample size thing doesn't tell you anything about what to do with alpha, but it says whatever you're going to do, if you want to make the prior information content small, make beta small. And so a standard thing people do is they use a gamma prior where beta is equal to some small positive number epsilon, like 0.01 or 0.001. And then for convenience, they just choose the alpha parameter to also be equal to epsilon. And they pick that for convenience because the prior mean then turns out to be 1, because you remember the mean of a gamma is alpha over beta. So a kind of a knee-jerk convenience prior that people gets used a lot and actually turns out to be abused sometimes. I'll show you later in the course that this is sometimes not a very smart thing to do. But in general, what we're trying to get at is this statement at the bottom here of page 11 that for my prior, I'd like to specify a member of the gamma family that's relatively flat in the region where the likelihood is appreciable. And a convenient and fairly all-purpose default choice of this type is what people call the gamma epsilon epsilon prior for some small epsilon like 0.001.
Small alpha gives me the
Indeed, it does.
And bigger alpha.
Indeed, it does. So he's making a good point, which is where I was headed next. Let's imagine what the gamma epsilon epsilon prior looks like. So this is lambda going this way, and this is the gamma epsilon epsilon density for epsilon equals some number like 0.001. Well, just as he said, it has this unfortunate behavior that it goes up to infinity right here. And then what it turns out to do in the other direction is it tries really hard to be flat across the entire positive part of the real line. So that turns out to be what the gamma epsilon epsilon prior looks like. Now, why does it do this nasty thing here? Well, it does it so that the integral is 1. It's got to be a proper prior density, and so it doesn't have much mass out here, so it shoves all the mass right there. Why, by the way, if we were trying to create a prior that was flat in the region where the likelihood was appreciable, why didn't we just use a uniform prior from 0 to infinity? Well, in fact, you might even end up with something that is incoherent in De Finetti's terms, because the analog of a flat prior that's literally flat in the Bernoulli case is the uniform distribution on the interval 0 to 1. So you could say to yourself, if I'm going to try to be relatively diffuse, as we did in the Bernoulli case study, why not be uniform from 0 to infinity? And the answer, of course, is that is an improper prior distribution. It integrates to infinity, so the area underneath it is infinite. And so far, I've mentioned to you that if you are a neophyte in the Bayesian paradigm, you should try to avoid using improper priors because sometimes they can lead to improper posterior distributions, and that's a way to say that you have created a Bayesian analysis that is a calamitous failure. By trying to be relatively diffuse, we may have shot ourselves in the foot. Now, it happens on this problem that it works okay, that this particular prior does work okay. And in general, when the parameter you're working with is a location parameter, like this one here, which specifies the center of the distribution, then of the Poisson distribution, then improper uniform priors like that do turn out to work fine, even for quite small sample sizes. But when you're working with parameters that have the nature of a scale, a variance or standard deviation, or later on we're going to talk about the reciprocal of the variance, which Bayesians call the precision, putting an improper prior on the precision or the standard deviation or the variance can lead to improper posteriors sometimes. And there are other problems where, with other different kinds of parameters where this can also lead to problems. So what the gamma epsilon epsilon prior is trying to do is it's trying to achieve something that's quite a lot like that, in that it's very close to flat across the entire positive part of the real number line, except that it has to tuck some of the probability here close to 0 because it has to go somewhere to have an integral of 1.
Why couldn't maybe rule without 5 prior assumptions, but uniform without for a year?
Yes. And so what he's suggesting is if you're having trouble with the uniform from 0 to infinity prior, then why not instead just use the uniform prior from 0 to some number c? And now we can start thinking about what that number c should be. I'll call it capital C to distinguish it from our irrelevant normalizing constant. And the answer is, if you want the prior to be not very influential to describe the fact that you don't know much external to the data set, then all you have to do is locate where the likelihood function is appreciable and just make sure that the c is big enough not to truncate the likelihood function. So go ahead and plot the likelihood function and see where it starts to run out and not matter very much, be really close to 0 to the right of that place, and just pick your value c to be somewhere out there. Obviously, if I picked a value of c right here, that would defeat my purpose because it would truncate the posterior distribution. If I picked a value of c over here, it would be even worse. So you just have to plot the likelihood function and see where it stops being appreciable in the right tail and pick a value of c, capital C, that's big enough to not truncate the likelihood function. And I'll show an example of that in a minute. Longer than, yeah, so we could have it go from 0 to 365 because the outcome variable here is, that's true. And that's something we know external to the data. That's correct. Now, does it sound to you like some kind of using the data twice to plot the likelihood function and see where it stops running out and then choose your value of c to make sure you don't truncate it? That does sound like some kind of using the data twice, but it turns out to be a kind of using the data twice that has no effect. It does not actually cause you to exaggerate how much you know. It's just a kind of technical convenience to approximate the thing he was describing. We know it should be uniform C, where C is some relatively big number, and you can do a sensitivity analysis on C and find out that once you get to any number you want that's beyond where the likelihood function is appreciable, it doesn't change the answer one bit. So here's the gamma epsilon epsilon prior on the interval of lambda from 0 to 4. And it looks as I described it to you before. Now I'm wondering where the likelihood function is appreciable. And so we know that it turns out the sample sum in this data set is 29 when you add the 14 numbers together. Oh, I'm sorry, I'm on the, yeah. So this is what the gamma epsilon epsilon prior looks like for epsilon equals 0.001 as lambda runs from 0 to 4. And so now I'm wondering to myself, where is the likelihood function going to be appreciable? And in fact, we know that the likelihood function behaves like a gamma density with parameters 30 and 14 because that corresponds to alpha plus, the alpha minus 1 thing is 29, and so alpha must be 30. S was the sum of the 14 numbers in the data set. You remember the mean was around 2.1, and so 29 over 14 is indeed around 2.1. So I can work out from the formulas for the mean and the variance of the gamma density that it has a mean of about 2.1 and a standard deviation of about 0.39. Now I know this distribution is the likelihood density is not going to be perfectly normal because with a small sample size it's going to have a long right-hand tail, as you've seen lots of gamma densities do. But there's this thing that you may have heard of, may or may not have heard of before, that I always teach in my intro stat classes called the empirical rule. And what the empirical rule says is, interestingly, pretty much no matter what the distributional shape looks like, if you start at the mean of a data set and go one standard deviation either way, you'll almost always get around the same percentage of the data. And that percentage is almost always around 2/3. So start at the mean and go 1 either way, you're going to get around 2/3 of the data, almost independently of the shape of the distribution. It's quite remarkable how well this rule works. That's part 1 of the empirical rule. Part 2 says start at the mean and go 2 standard deviations either way. Then what you'll find is that you'll get most of the data, where most turns out to be around 95%. And part 3 of the empirical rule says start at the mean and go 3 SDs either way. You'll generally get almost all of the data, where almost all means a number on the order of 99%, 99 and a bit. And of course, the famous number from the normal curve itself is 99.7 for 3 and 95% for 1.96 and when you start going either way for one standard deviation, either way, the normal curve number is 68%. So here is the empirical rule written down on one of these pages of handwritten notes. So start at the mean for almost any distribution. If you start at the mean and go 1 SD either way, you'll capture about 2/3 of the data. 2 SDs gets you most of the data, about 95%. 3 SDs gives you almost all of the data, 99%. So returning now to this calculation on this page of the PDF notes, if the mean is 2.14 for the likelihood density and the standard deviation is 0.39, I could go 3 of those SDs either way and get a value like about 1.2. And so go roughly 1.2 either way from 2.1, and that will go down to about, what is that, 0.9 and up to about 3.3. So by the empirical rule, the likelihood should be appreciable in the range from roughly around, I guess, around 1.0 up to 3.3. And look, you can see in this plot that indeed it's true that for this particular gamma epsilon prior, the likelihood is indeed, rather the prior is indeed relatively close to flat in the region from about 1 to about 3. See how it has a little bit of downward curvature, but not enough to matter very much. And so this will be, in fact, a diffuse prior for this particular problem. What could go wrong in using the gamma epsilon prior? Well, look at the picture here. What if the likelihood function had significant mass near what? Near 0. Then you'd actually be piling on, wouldn't you? Because the prior would say there's a lot of prior weight for lambda values near 0, and the data weight would have a lot of values near 0, and you'd end up actually putting in a highly informative prior when you didn't mean to. So the way to use this prior is with a little bit of care. You have to think about, use something like the empirical rule to work out what the range in which the likelihood function is appreciable will be, or equivalently, just go ahead and plot the likelihood function, and then make sure that the gamma epsilon prior that you're interested in is indeed relatively flat in the region where that particular likelihood function is appreciable, and then you have indeed achieved a relatively low information prior. Or you could do what we were saying before. You could plot the likelihood function and use a uniform prior from 0 to some number capital C that is big enough to avoid truncating the likelihood function. So from the Bayesian updating, so I'm okay with this prior now, and with the Bayesian updating that we've seen, with a gamma epsilon prior, the posterior is almost exactly like the likelihood function. Now it's gamma with parameters 29.001 and 14.001. And so as I have shown you in the previous case study, it's useful in summarizing the updating from prior to posterior on the way, with the likelihood on the way, to make a table that records measures of center and spread at each point along the way, and then also supplement that with a plot of the prior and the likelihood and the posterior on the same graph. So, for example, here the gamma epsilon prior with epsilon equal to 0.001, when regarded as a density for lambda, has mean 1.0 and standard deviation equal to 1 over epsilon, which is square root of 1 over epsilon, which is 1 over 1,000, which is about 32. And so that's like saying, as far as we're concerned, before the data arrive, lambda, the mean length of stay for this kind of these kind of women who were giving birth to premature babies, could be more or less anywhere between 0 and, let's say, 100, using the empirical rule, going up roughly 3 standard deviations from the mean. The gamma posterior with parameters 29.001 and 14.001 has posterior mean given by a value which is almost exactly equal to the sample mean, and posterior standard deviation equal to roughly 0.385. So after the data have arrived, we know quite a bit more than before. The prior standard deviation was about 32 days of length of stay, and now the posterior standard deviation is only about 0.4 days of length of stay. So we've learned quite a bit from only 14 observations. It turns out that there are 2 different ways to summarize the likelihood. Fisher's approach based on maximizing it, which we looked at a lot last time. And then there's the Bayesian approach based on regarding it as a density and integrating it. And it's actually useful to compute them both and compare. So the likelihood integrating approach, which also was examined by Fisher, although he was not willing to admit that's what it was. This is that thing that a few times ago I think I called fiducial inference. Basically, if you treat the likelihood function as like a posterior distribution, that's the same as treating the problem as Bayesian where you use the uniform prior distribution. Then the likelihood would, of course, be exactly equal to the posterior. And Fisher is then able to go ahead and do integrating over the parameters and get out all sorts of probability statements like we do as Bayesians, but basically all he's doing is Bayes with a uniform prior. This approach would treat that gamma likelihood with parameters 30 and 14 as a density for lambda, with mean 2.14 roughly and standard deviation about 0.39. And then with the maximum likelihood approach, we have the likelihood function earlier. So now the log likelihood function involves just taking the log of that. And so the log likelihood function behaves like S log lambda minus n times lambda. And there's an arbitrary constant that could be added or subtracted from that, but we might as well take that constant to be 0. And so, as usual, we do the usual arithmetic where we take the first partial of that log likelihood function with respect to lambda and set that derivative equal to 0 and solve. And an extremely simple equation comes out in which the MLE is just S over n again, the same as it was in the Bernoulli case study. So in the Poisson model, the maximum likelihood estimate is just the sample mean. Now, here's an interesting point. Since the MLE turns out to be our old friend, the sample mean y bar, you might be tempted to conclude immediately that the standard error of the MLE was our old friend sigma hat over the square root of n, which is the formula we always use when we have Gaussian data, where sigma hat equals 1.54 is the sample standard deviation. And indeed, it is true in repeated sampling that the variance of y bar does behave like the variance of any one of the observations over n, because it's a mean, and that's how the variance always works with means. But the Poisson distribution has variance also equal to lambda. So that actually the square root of the variance of y bar in this problem is actually the square root of lambda over the square root of n, not sigma hat over the square root of n. And there's no guarantee in the Poisson model that the best way to estimate the square root of lambda in this standard error calculation is with the sample standard deviation sigma hat. In fact, look back at the likelihood function. Do you see the sample standard deviation appearing anywhere in that likelihood function as part of the vector of sufficient statistics? Is anybody telling you anything about calculating what we usually do to get spread, the sample standard deviation? The answer is no, it doesn't appear there at all. The only function of the data that matters is the sum, or equivalently the mean, of the observations. So your knee-jerk thing to say was, well, go ahead and just use, since it's a mean, just use sigma hat over the square root of n, where sigma hat is the sample standard deviation. But actually, from an information processing point of view, that's the wrong standard deviation. We really need to use the actual variance of the y's, which is lambda, and so we're going to need to use square root of lambda hat as the right estimate of the standard deviation here. And we find that out by going ahead and doing the Fisher information calculation. So now I compute the second derivative of the log likelihood function, and I hit that with a minus sign and evaluate it at the MLE, and that turns out to be n over y bar, and so the repeated sampling approximate variance turns out to be y bar over n, which is the MLE over n. So this shows that sigma hat over square root of n is an absolutely irrelevant formula, and that's the reason it is that the only model in which that's the relevant thing to do is the Gaussian, in which it's the exact relevant thing to do is the Gaussian, and we're not thinking of the data as Gaussian at all. Obviously, we're thinking of the data as Poisson. So in this case, Fisher's likelihood maximizing approach would estimate lambda by the MLE, the same number we got before, give or take, given by the square root of the repeated sampling variance, the reciprocal of the Fisher information. That comes out about 0.385. So you can bring this all together in this little table at the top of page 15. The first row gives either the mean or the estimate, and the second row gives either the standard deviation or the standard error. In the Bayes world, we would talk about the prior and likelihood and posterior means, and the prior and likelihood and posterior standard deviations. In the frequentist world, we would talk about the prior and likelihood and posterior estimates, so to speak, if you want to think of it that way, and standard errors. So if you look at the table, the prior has a mean of 1 and a standard deviation of 32. The posterior has a mean of about 2.071 with a posterior standard deviation of about 0.385. And the likelihood maximizing approach has given exactly those same numbers and the likelihood integrating approach is given almost exactly those same numbers. And the discrepancies, the small discrepancies you see between the likelihood maximizing and likelihood integrating columns in this table are a function of the fact that we only have 14 observations, and those discrepancies would disappear as the sample size grew. So here's my prior likelihood posterior plot in this particular problem. I'm doing it in Maple again. So I plot the function p of lambda, and I give it 3 different functions to plot with different values of the alpha and beta parameters. And it looks initially as though there's only 2 functions plotted, because that seems to be all you can see. But actually, Maple has chosen to plot the prior distribution by showing you a little teeny hint of its curvature right down there near 0, and then it doesn't bother to show you the part where it blows off. That would influence the vertical scale of the picture. So it did something smart. It worked out that the right vertical scale of the picture was driven by the likelihood in the posterior, and the gamma epsilon prior at a point that corresponds to not explode any further up vertically. So the prior is practically negligible in this drawing, in the sense of it being really close to flat in the region where the likelihood is appreciable. And you can see that indeed the posterior and the likelihood are quite similar to each other, as we'd expect with this sort of diffuse prior analysis. Now for interval estimation, so the standard likelihood thing to do would be to use the MLE as your point estimate. And the standard thing from a Bayesian point of view, if you had to use a point estimate, might be to use something like the posterior mean, which will be close to the MLE here. But for interval estimation, in the Bayesian approach, you just write down the posterior distribution and go 2.5% into each tail, and you're done. That's your distribution. So in the Bayesian way of looking at this to construct an interval estimate, you would draw the posterior distribution, which has a long right-hand tail here, and you would find the place that has 2.5% of the area in the left tail, and the place that has 2.5% of the area in the right tail, and that number would be your left and right endpoints of the interval, which you have a 95% interval in the middle. And it literally would be a correct posterior probability interval for the parameter lambda, because in the Bayesian world we can talk about that sort of thing. There is another way to do this sort of thing. This is called the equal tails way to summarize a posterior distribution. Another way to summarize it, let me try to draw it again as this long right-hand tail guy, would be to say, let me start drawing, oh, I'm sorry, down a little too far. Let me start drawing horizontal lines and notice where they connect, notice where they hit, and start asking how much of the area in the underneath the curve from there to there is captured in that range. And move the height of your horizontal line around until you find 95% in the middle. That's called the highest posterior density way of computing interval estimates. Highest posterior density, or HPD for short, HPD, highest posterior density interval. In this case, it'll be an interval, or another name for it is to talk about the HPD region in more than one dimension. And in this problem here, the equal tails approach and the HPD approach would give slightly different answers, but there wouldn't be enough in it to be worth bothering over. If the posterior distribution is very skewed, they're going to give different answers. And you would have to do a little simulation study to see which one had better repeated sampling behavior to decide which one you wanted to use in your problem. At least that's how I would approach making the choice. Now you can see that the likelihood function is skewed here. The standard large sample maximum likelihood thing to do would be just to appeal to the central limit theorem, even though we probably we aren't yet at the normal curve. In fact, we can see from that plot that we're not. If I were to, you can see even at this scale, if I were to blow it up by showing you the range from 1 to 3.5, which is where most of it lies, you'd see even more clearly that it's asymmetric. So the central limit theorem is not kicked in yet. But if you pretended that it did, what Fisher would have told you to do here is just start at the MLE and go 1.96 estimated standard errors either way, and you would get an approximate 95% confidence interval for lambda in which the approximation would come from two things. One is that the data might not really be from a Poisson distribution. The other thing is that you're using an asymptotic, a large sample result, when you only have 14 observations. A better way to do it would be to go ahead and extract those 2.5% points and so on. And so I've shown you how to do that in Maple. And so the 95% central posterior interval or equal tails interval given a diffuse prior runs from 1.387 to 2.890. And you can see those numbers are a bit different. 1.316, 2.826, they're a bit different from the maximum likelihood story. The Bayesian answer is correctly asymmetric about the posterior mean because we still have skewness in the posterior. I see it's time for our next break, so let's break again, and I'll start again at 11:30. So let's begin again. Video people, if things have been off for a while, we can turn them back on again now for the next hour. So I'm still on page 17 of the handout on part 2B of the course. I showed you rather more quickly than I should have just before the break. You can do numerical integration in Maple to find the upper and lower limits of the interval that we're interested in here. If I asked Maple to do this integration in closed form, it would be unable to do it except in terms of expressing the result in terms of the integrals of the gamma function. But if I say EVALF, that stands for floating point evaluation of the integration with a capital I, that tells Maple that I want it to do a numerical integration. And I made a first guess of 1.316 and found that there was on that much area, about 0.013 in the left tail. So then I guessed a little bit bigger number, 1.4, and got too much. And eventually, after a bit of iterating, I got 0.249, and then similar sort of thing in the right tail. You can do it much more quickly in R, actually, if you master the gamma package in R. So Q gamma gives you quantiles of gamma distributions. So I ask R to give me help on the Q gamma function. And here's what it says. As usual in R, there are 4 different members of any distributional family. D gamma gives the height of the density at a particular point. P gamma gives the cumulative distribution function values to the left of a place. Q gamma gives the quantiles or percentiles. And R gamma allows you to sample randomly from the distribution. And you will note the following thing. It regards the first parameter after the input to the functions as the shape parameter. And the second one is what it calls the rate parameter. And the third one is what it calls the scale parameter, which is 1 over the rate. And so what it's trying to do is to cover both bases for how people think about that beta parameter in the gamma distribution. And to see what's going on, we always have to read through the details and see what it thinks the density looks like and what it thinks the mean and variance are. So it thinks the density function is 1 over s to the a times gamma of a, all in the denominator of the fraction, x to the a minus 1, e to the minus x over s. And you'll note that's not the same as the parameterization I used in the version I'm using here. The x to the a minus 1 part is fine. That corresponds to our lambda to the alpha minus 1. But we had e to the minus beta times lambda rather than e to the minus the argument over s. And so basically, built into R is the idea that the way it's parameterized things is the reciprocal of the way I parameterize the scale parameter in the way we're doing things. And this is a source of much grief for people trying to use this function, because if you just jump into it and don't pay attention to exactly the parameterization R does, you can get out really absurd results naturally if the right answer was to take the reciprocal of something and you put in the other number instead. So here's a warning on this page. There are 2 common parameterizations of the gamma distribution. The one as in equation 6 above, which is the beta to the alpha over gamma of alpha, lambda to the alpha minus 1, e to the minus beta lambda. in which 1 over beta is the scale parameter, and one as in R, in which the scale parameter S is equivalent to 1 over the beta that I'm using. And the easiest way, as I've just shown you, to see which parameterization someone's using is to force them to write down their idea of what the gamma density function looks like. If it looks like the thing I've got there, then 1 over beta is the scale parameter, whereas if it looks like what R is using, then S is the scale parameter. And of course, the other dead giveaway is to ask what the mean and variance are. If the person you're asking is using my formula, the answers are alpha over beta and alpha over beta squared, whereas if that person's using the R representation, then they're going to get A times S, not alpha over beta, and A times S squared, not alpha over beta squared. So in order to get the things I want here, I have to say Q gamma of 0.025. Please find the place on the gamma distribution with the parameters I'm about to mention that has 2.5% of the area to the left of that place. With parameters 29.001, that's the shape parameter alpha, and I could say comma scale equals 1 over 14.001. That'll force R to do the right thing. Or if you saw back here, it has this option called rate equals 1, scale equals 1 over rate. So I could have put in rate equals my number 14 point whatever, and it would have gotten the right answer that way as well. So there you go. So that's how to get the quantiles of the gamma, and it matches the numbers I got from Maple, of course. And in fact, we can also see how bad the likelihood interval is. It's symmetric, and it shouldn't be symmetric. But it turns out it's done a kind of a balancing. It's tried to come up with about the right coverage, even though it's being incorrect by being symmetric, because I can ask Maple to work out what is the actual probability content of Mr. Fisher's symmetric interval, and it does come out to be pretty close to 0.95. So here, the maximization approach has led to reasonably decent approximations, although later I'll be giving you some examples where maximum likelihood doesn't do so well. Now, what if we wanted to predict the next observation? I'm about to argue that this is an important thing to do in order to check the model. And so you remember the logic of how we compute these things. So I'm looking now at the steps in equation 14 on page 19 of the handout 2B. So step 1, we look at the left-hand side and we say, I want to know the predictive distribution for yn plus 1 given the data I've seen so far, y1 through yn. I notice that's hard to think about, and I remember that trick that I showed you before, which was when things are hard, try to introduce something else into the conversation that makes things easier. And so here, all of these things are about data. It would certainly make things easier if we knew what lambda was. The true value of lambda would tell us lots of things of useful here. So on the first line of equation 14, I say, well, I'll use the law of total probability. The predictive density on the left-hand side is equal to the integral of the joint distribution of yn plus 1 and lambda integrated over all lambda values. So that's just saying the exact same thing as the left-hand side. Another way to put it is that you could take the right-hand side, and by integrating over lambda, you have gotten rid of it in the integration process, and you've done what's called marginalizing over lambda, and the result must be the left-hand side. So that's step 1. And that's already a great thing because it's introduced lambda into the conversation. But it isn't quite ready yet because we don't know anything about the joint distribution of yn plus 1 and lambda given y. We know things about the behavior of yn plus 1 if we knew what lambda was. And so what we want to do next is to force lambda to migrate over to the other side of the conditioning bar. And so I replace in the second line of equation 14, I put the lambda where I want it to be, namely p of yn plus 1 given lambda and y. And then I just work out using the definition of conditional probability what has to sit next to it multiplicatively in order for the equation to still be correct. And as you recall, perhaps from our earlier discussion, that has to be the posterior distribution for y, given the data so far. So the second line is a great improvement over the first line because now lambda is on the correct side of the conditioning bar as far as the yn plus 1 is concerned. And now we make that jump that we talked about a bit maybe 2 weeks ago. That's an important jump in the Bayesian story. Let me remind you of the story. We were looking at a stream of ones and zeros that you and I are both willing to agree is a Bernoulli process that behaves like conditionally IID given theta, and we don't know what theta is. Now I show you that the first 10 results of that process involve 7 ones and 3 zeros, and I ask you, is that information in the data vector y1 through y10, is that useful to you to predict the next data element? And what did you guys say 2 weeks ago? Answer, yes, because you don't know what theta is, and so you use the information in the first 10 draws to estimate theta, and that helps you predict the 11th one. But now, in a completely different set of knowledge, if somehow, as from a stone tablet down from the sky, you knew that theta was equal to 0.6, and I offered you, in addition to that knowledge, the information that of the first 10 observations, 7 of them were 1s and 3 were 0s, would that extra data information change your prediction of the 11th observation? If you knew what theta was, the answer is no. You would throw away the data and say that my predictive distribution for the 11th observation is Bernoulli with theta equals 0.6. Thank you very much, right? So now on the step 3 in this equation, we do the same thing. I want to ask you to predict yn plus 1, given the truth about lambda and also all the previous data so far. And by the same exact reasoning we just went through, you say, well, actually, that's very nice of you to offer me both lambda and y, but I don't need y in the presence of lambda, so I'll just toss it out. So the third line becomes simpler, and it's now the predictive distribution for yn plus 1 given lambda, but that's just equal to our sampling distribution. That's what we usually call the sampling distribution. If you know what the parameter is, then we call it the sampling distribution. And of course, the Pasteur distribution is that particular member of the gamma family that we worked out in the Bayesian updating. So now we get a kind of nasty looking integral. I just stuff in the sampling distribution for the next observation. It's a Poisson, right? So I stick it in the Poisson form, lambda to the yn plus 1, e to the minus lambda over yn plus 1 factorial. And then I stick in the Pasteur distribution, which has to look like some kind of beta to the power some kind of alpha. Here I'm calling them beta star and alpha star, where beta star and alpha star are the updated values in the Pasteur, alpha star being alpha plus s and beta star being beta plus n. You have that normalizing constant times lambda to the alpha star minus 1, e to the minus beta star lambda. That's the usual gamma expression. Now I pull all the stuff that doesn't involve lambda out of that integral and stick it in the front and collect all the remaining terms together. And hey presto, I have another gamma integral. Look, it's of the form lambda to some positive power, e to the minus some positive number times lambda. So that's another gamma integral. And Maple certainly knows how to work out that integral, and even you and I could do it from the basic integral that gave rise to the normalizing constant if we had to. But here I'm going to go ahead and just let Maple do it for me. I'm as lazy as the next guy. So let's do it like this. I say, Maple, please assume that A star and B star are both positive and that the y future value is also positive. And now simplify, please, for me. B star to the A star over that stuff in the front times the integral that I want. And Maple comes out and gives me the exact expression. So that's the predictive distribution in closed form. It just does the integral correctly for me in closed form. Now I'll rewrite it in LaTeX and rearrange things a little bit. That's the predictive distribution for the next observation given the data so far. The lead term is a ratio of things that involve products of gamma functions. And then we have beta star over beta star plus 1 to the power alpha star times 1 over beta star plus 1 to the yn plus 1. That's my predictive distribution. You will have never seen this distribution before, but it actually has a name. And the name comes from the fact that the way we computed it is that we calculated an integral that was a mixture. Look how, if you look at the line 4, or even just line 3 of equation 14, this says take a weighted average or mixture of the Poisson sampling distribution weighted by a gamma distribution. See how P of lambda given y is the weights, because it's a density that adds up to 1. So it's like taking a weighted average. And the particular P of y given lambda here is a member of the gamma family, having used the gamma prior as a conjugate. So this says take a weighted average of Poisson sampling distributions weighted by a gamma distribution. And so people call it the Poisson dash gamma distribution. And they mean by that it's a mixture distribution. We're taking a gamma mixture of Poissons. So there it is. It's actually related to a distribution you may have studied before. It's a generalization of the negative binomial distribution. And a very useful generalization of the negative binomial distribution. Maple, I can try to use Maple to get simple expressions for the mean and the variance. And I've shown you a number of examples here where Maple really helped and got the right answer in symbolic form. Here, Maple got it half right. So here I define a density called the Poisson gamma function, PG, It maps y, alpha, and beta onto that expression I showed you before. I ask it to do a symbolic integration of that thing as y goes from 0 to infinity, and now remember it's an infinite sum because this is a predictive distribution for integers, yn plus 1 being 0 or 1 or dot dot dot. So this is adding up. This is a probability mass function, not a probability density function. So I asked Maple to work out what the infinite sum is, and it says 1 under the assumption that I made earlier that alpha and beta are positive. Then I ask it to work out the mean and simplify it, and it says, okay, it turns out to be alpha over beta, which is kind of interesting. That's the same mean that we had in the posterior distribution for lambda. So the mean of the distribution in this predictive is alpha star over beta star. And then when I ask it to work out the variance, it gives me back a closed form expression, but it's a hideous closed form expression involving the hypergeometric function, which is a function that you do not want to go anywhere near if you can possibly avoid it. So either I haven't told Maple enough background information about what's really going on here, or else it didn't do a good enough job of simplifying, because you can look in other reference books. For example, the excellent book on Bayesian theory by Bernardo and Smith points out that that variance just has the following simple form. It's alpha star over beta star times 1 over 1 plus beta star. Yes. When you say sum, blah, 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 comma, argument equals 0 dot dot infinity, it knows correctly that that's supposed to be that the index of summation is the y, and the range of summation is the integers from 0 to infinity. That's a correct way to write it. Otherwise, it couldn't have got this expression correct for the mean. That is because it's a sum. If I said the word int for integration, it would think that it was a continuous integral. So this turns out to be a nice closed form expression for the predictive variance, and I can make a little table in which I contrast inference on the one hand and prediction on the other hand. We know already that the posterior mean of lambda is alpha star over beta star, and the posterior variance is alpha star over beta star squared. And writing out what those are in terms of the prior parameters alpha and beta and the data parameters s and n, you're able to make a little table like this. And I find this table quite interesting. I'll try to explain why, and I hope at the end of the explanation you will also. Not knowing lambda and trying to learn about it is called inference, because lambda is an unobservable parameter in a model. We're never going to get to find out what lambda is until we wait to die and go to heaven and talk to St. Peter. Yn plus 1, on the other hand, is an unknown that's observable. And so the operation of quantifying your uncertainty about observables we've agreed to call prediction, as distinct from quantifying your uncertainty about unobservable parameters. That's called inference. So the first row of this table describes your inferential uncertainty in the posterior as measured by the mean and the variance. And the second row measures your uncertainty about the predictive distribution in the posterior as measured by the mean and the variance. And it's kind of interesting to notice that your posterior mean for the unknown lambda and your posterior mean for the new y that you're going to get next are the same, but the posterior variances are not the same at all. And they have an interesting form. One of them can be written as alpha plus s over beta plus n times 0 plus 1 over beta plus n. The other one can be written as the same thing except plus 1 times 1 plus 1 over beta plus n. And that, in turn, is exactly the central distinction between inference on the one hand and prediction on the other hand, as I will now try to explain. Which of those posterior variances is going to be bigger? Alpha and s and beta and n are all positive numbers. And so which one has to be bigger? The inferential variance on lambda or the predictive variance on yn plus 1? The predictive variance. And in fact, that makes sense, right? If you're trying to predict what the next observation is, and you know that if you knew what lambda was, it's a Poisson, then your predictive uncertainty actually has two parts to it. First comes your inferential uncertainty about lambda, and then comes your predictive uncertainty about the next observation if you knew what lambda was. And so the combination of those two sources of uncertainty means that your predictive uncertainty has to be bigger than the inferential uncertainty by itself. And in fact, the way that it's bigger is quite interesting as follows. So like it says here, thus lambda, the inferential objective, and yn plus 1, the predictive objective, have the same posterior mean, but the posterior variance of yn plus 1 is much larger, as can be seen by the following argument. Let's denote by mu the mean of the population from which the yi are thought of as like a random sample. I'm going to now refer you to what you know about means as distinct from thinking about things as Poissons. So mu is the mean of the population. That acts like lambda here. When little n is large, alpha and beta will be small in relation to s and n. And so the ratio y bar equals s over n should more and more closely approach that number mu. And so for large n, the posterior mean for lambda given y should be the same as the posterior predicted value for yn plus 1, the mean of the posterior predictive distribution for yn plus 1, and they should both be close to mu. But for the Poisson distribution, the population mean, mu, and the variance, sigma squared, are equal, meaning that for large n, the ratio alpha plus s over beta plus n will be close both to mu and to sigma squared. Thus, for large n, we know that the variance of a mean is given by sigma squared over n, where sigma squared has this special expression lambda in the case of the Poisson, but the predictive variance of the next observation behaves like sigma squared, not sigma squared over n. And so an informal way to restate this new expression is that accurate prediction of new data is much harder than accurate inference about parameters. Because look what happens to those two expressions in equation 18. As you get more and more data, what happens to the posterior variance? It goes to 0. But as you get more and more data, does the posterior variance of the next observation go to 0? No. It goes to a constant value, which represents that kernel of uncertainty that you have about the next observation, even if you knew what lambda was. So that's basically what's going on here. In fact, if you look back at these two parts of this formula, that's exactly what's happening. The first term in the inferential part says alpha plus s over beta plus n times 0. So that means nothing going on there. And the next term means alpha plus s over beta plus n times 1 over beta plus n. And look, the beta is going to be small relative to the n when n is big. So that's like some quantity over n. In other words, the variance is going to 0 at a 1 over n rate on the variance scale for lambda. But look at the corresponding expression for the variance for yn plus 1. The thing outside the parentheses is getting closer and closer to the true mean. And the thing 1 over beta plus n is going to 0. That's the uncertainty that you have about the parameter. But the predictive uncertainty about the next observation is never going away. So the difference between the 0 plus that stuff and the 1 plus that stuff means that prediction is inherently a more difficult thing to do than inference, in the sense that your predictive uncertainty will never go to 0. Your inferential uncertainty is order 1 over n. But your predictive uncertainty is order 1, which means that it doesn't go to 0 as you get more and more data. That's just the way the world is, right? If you're really trying to predict the future, there will be two components to your uncertainty, even if your model is right. Your uncertainty about your parameters and your uncertainty about the future, even if you knew what those parameters were. And you can never make that second component of uncertainty go away. Now, as a by the way, I have written some code to evaluate the Poisson gamma function, density function, or probability mass function here on the course web page, and you can download that and play with it if you like. If you look back at the formula for it, you'll see that you are very ill-advised to try to calculate this thing directly from those expressions, because as soon as alpha and yn plus 1 start getting fairly large, those gamma functions are going to start getting really big. And the gamma function blows off to plus infinity really fast. And so whenever you've got gamma functions in an expression, particularly when they enter multiplicatively, right away you think of taking logs to improve numerical stability. So a much better way to evaluate this predictive distribution is to take its logarithm, evaluate the log, and then exponentiate at the end. And R has not only the gamma function built into it, but it has the log gamma function built in also. It's called LGA-MMA. And so the safe way to calculate this probability mass function is to take its logarithm, evaluate the logarithm, and then exponentiate at the end. And so that's what I've done in the R code. Log.density is given by a sum of a bunch of terms because everything was products before that. And so you calculate the log dot density and then return e to the log density. That's got to be a much safer way to do things. Okay, so now the whole point of constructing a predictive distribution, well, there's two real points to constructing predictive distributions in the Bayesian world. One is that it's actually really good to be able to predict future observations, right? It may well be that the entire modeling goal in your stochastic modeling exercise is to predict future observables. If you're trying to decide what decision to make, how to behave in the future, to hedge against your uncertainty in the appropriate way, and then the predictive distribution for what observable thing is going to happen in the future is ideal for you to help decide what to do. So it's a central operation in Bayesian decision making. And it's also a central operation in Bayesian model checking for the reason I said before. Good models make good predictions of observable things. Bad models make bad predictions. That's one important way that we know whether we have a good model or a bad one. So one way to check a model like this Poisson model is as follows. I have a little for loop here in which the steps are described in words rather than in R code, but it's easy to translate into R code. One idea would be just to go ahead and calculate the predictive distribution, the height of the predictive distribution for each of the data values in the data set, where the posterior predictive is based on the entire data vector. But that would actually be subtly using the data twice, because you would be using the whole data vector to create the posterior distribution for the parameters, and then you would be evaluating how well each observation fit into that predictive distribution, but you already used that observation to help decide what the distribution should be. So that's a kind of gentle version of using the data twice, in which I use the entire data vector once, and then I also use a little piece of the data vector again to see how good things are. You could remove even that little bit of using the data twice by a cross-validation style idea like this gentleman said a while ago. Why not do the following thing? Why not set each observation aside one by one and compute the predictive distribution for it given all the rest of the data, and then compare the actual data value with what you predicted for it given the rest of the data? Has anybody ever seen anything in statistics where you take a data vector and leave one observation out and then see what happens and do that for all the observations? It was invented by Tukey, and it's called the jackknife. So we're actually doing a form of cross-validation in which we only leave one observation out at a time, and that's what Mr. Tukey called the jackknife. So this is a simple form of model checking. As I runs from 1 to n, temporarily set aside observation yi, obtaining a new data set, which I'm going to call y subscript minus I, which is the entire data vector with observation I set aside. So the vector called y sub minus I has n minus 1 observations in it. And now use the current Bayesian model applied to y sub minus I to predict the omitted observation y sub I, and then summarize the extent to which the actual value of y sub I is surprising in view of this predictive distribution. So we need to come up with some sort of quantitative measure of surprise in comparing an observation with a distribution. And you may never have thought about that operation before, but we can think about it together right now. Suppose, not in this problem, because our predictive distribution is going to be probability mass function. It's going to have points at 0 and 1 and 2 and so on, nothing in between. But suppose in another problem, like we're going to be doing after lunch, that your predictive distribution looked more or less like a Gaussian, for example. So this is your predictive distribution for the next observation given the data so far and the background information. How can you then go ahead and stick in where yn plus 1 actually landed, let's say it lands right there, and come up with a quantitative measure of how badly those two things are in agreement with each other, how strong the disagreement is. Or equivalently, you could come up with a number that represents how well they agree with each other. This requires coming up with a measure of distance between an entire distribution on the one hand and a point, a number on the other hand. And you may never been asked to think about that problem before. It's called, the process is called scoring, and meteorologists have to do it all the time because they have predictive distributions for what's going to happen on things like temperature and wind speed and things like that, and they actually get to compare what happened with their predictive distribution for it, and so they're one of the most prominent sets of scientists who are faced with this issue all the time. Well, one thing that comes to mind is you could create something that you could call a predictive z-score, right? So I could write down here's the mean of the predictive distribution given the data and the background, and I could work out the standard deviation of this distribution. I could call that number S, and I could call this number let's call it S star, and let's call this number mu star. So I could standardize that number, right? I could convert it to standard units by calculating yn plus 1 minus mu star over S star, right? And that would be a z-score. And then I could do that for each observation and look at the z-scores. And an informal thing to say is that if my predictive distributions are good, then these z-scores should behave roughly like you'd expect from draws from a standard normal distribution, because that would mean that I got the mean approximately right, and I also got the standard deviation approximately right. And so once I'm done doing this, I could calculate these predictive z-scores and get their mean and standard deviation, and maybe plot them on a normal QQ plot, for example, and see if they look like draws from a normal distribution. So that would be an informal thing to do. There are better things to do, which we will look at later in the course. The best thing turns out to do, people have invented rules that govern what is called optimal scoring. And what you would do there is you would, just like Mr. Cox did in developing his optimal information processing through Bayes' theorem, you would invent principles for what a good scoring rule should look like, and then you would try to find the best scoring rule that focuses on those principles. And it turns out that from a number of different points of view, the best thing to do is to pay attention to the height of the predictive distribution at the data value that actually occurs. So you're supposed to compute the actual height of the predictive distribution at that particular point. Let's call it yn plus 1 star. So you work out the height of the predictive distribution, or let's just call it y star. You work out the height of the predictive distribution at the point that it actually obtains. And then the right thing to do in order to give the proper weight to each of the data points is out to work with the logarithm. And so this rule here is called the log scoring rule. And I'll be describing a very good way to tell when one model is better than another model from a Bayesian point of view later in the course based on this log scoring idea. The absolute value of this one, the z-score here, down here at the bottom, because I would like to have a healthy pattern of predictions that are below the predictive mean and above the predictive mean. So I really do want to pay attention to the plus and minuses. I would like these z numbers to behave like draws from a standard normal. So I'd like half of them to be negative and half to be positive. That would be a way of saying that my predictive mean was about right. And so, like it says back here on the PDF, one possible measure of surprise is predictive z-scores, where you calculate the observed value y sub I, doing this jackknifing thing. You calculate the observed value y sub I minus its predictive mean divided by the square root of its predictive variance. And then we can compare the surprise measure with its expected behavior. If the model had been correct, for example, we should hope that that vector of z-scores should have mean 0 close to 0 and SD close to 1. Why not? Yes, please. That's another idea you could do. That's right. You could now get quantiles based upon this thing and see how close the quantiles are to draws from the uniform distribution. But when we draw something like a normal probability plot, we're doing that in effect anyway when we calculate the normal scores. So no, you're right. That would be another way to go. At this here, I bet everybody in the room, if they thought about it for a while, could come up with a interesting, reasonable thing to try, because we are at the moment talking at a level of ad hocery within the Bayesian paradigm. There is no ad hocery in the Bayesian paradigm in the following part of it. If you have somehow decided that you've got a good specification of the prior and the sampling distribution, then there's no ad hocery about how to draw conclusions based upon that of an inferential and predictive nature. If, in addition, you specify what you regard as a good action space and a good utility function, there's no ad hocery about how to arrive at a good decision. You maximize expected utility. But there is still ad hocery in the Bayesian paradigm, as there is in the frequentist paradigm, in the important step that involves going from the real-world problem to those 4 ingredients I just mentioned. The mapping from the real-world problem you're starting with down to the prior, the sampling distribution, the action space, and the utility function. That is still something that has more ad hocery in it than I would like personally as a scientist. And I'm writing a paper right now with title Bayesian Model Specification, toward a theory of applied statistics. I believe if we had a better set of logical progressions from principles to axioms to theorems about how to do that specification in a way that we could agree is close to optimal, then we would be on sounder footing here. But at the moment, the fact that we are all now thinking about how to compare the observations with their predictive distributions in a somewhat ad hoc way is an example of the fact that we still have ad hocery, even in the Bayesian paradigm, in the important ingredient in specifying, going from the real-world problem to those 4 ingredients that are the inputs. And I'll have much more to say about that somewhere around week 7 or 8. We're going to be hitting that. So here's some R code to carry this out. And if you want to do it yourself, I've written some predictive checking code for you here and posted it on the web page so you can run this yourself offline in R. So I put in the Poisson gamma function, and I print the data vector. In this case, I'm going to sort it from smallest to largest and then print that. And I'll create an element called y.current, which is equal to, and conveniently, the notation in R for the vector with the first observation omitted is exactly the same notation as I used in the LaTeX a while ago. You say to R, y, open bracket, open square bracket, -1, close square bracket, and it knows that what you mean is the y vector with the first observation omitted. So that's kind of cool. So I now have a vector called y.current, and I have n.current, which is the length of that, namely only 13 observations now. Alpha and beta are both epsilon 0.001 in the diffuse prior. S.current is not the same as the sum of all the 14 observations in general, of course, because it's the sum only of the remaining ones with this one put away. It turns out to be the same here because the observation we just omitted was the 0. But anyway, S.current is the sum of the y.current values, and alpha star is alpha plus S.current, and beta star is beta plus N.current. And now I can calculate PG.current as a vector of I feed to my Poisson.gamma function the vector from 0 to 9 using the parameters alpha star and beta star, and it tells me what the height of those predictive distribution is at those integers from 0 to 9. And now I can plot the integers from 0 to 9 against PG.current, and I get this picture here at the bottom of the page. And actually, the way to make the picture work is I first have to plot it for, I use what's called type equals n in R, and what that does is it creates a null plot first, which is just essentially waiting for the actual plotting information. And then I write a little for loop in which I use the segment function to plot those little vertical segments that create what amounts to the histogram bars. And when you want to create something that you can put into a LaTeX document or some other document, you can spool the output of any graphics program into a PostScript file or a PDF file with the commands PostScript or PDF, and then you turn them off with the dev.off command. So that's how to get that all working. And so now informally, that's my predictive distribution for the observation 0, and I can ask myself, does 0 look unusual in that distribution? And in fact, the answer is, well, it's not the most likely number there. The most likely number is 2, but 0 is actually not that unusual in that distribution. And in fact, its predictive z-score is only about minus 1.4. And even with a sample of size only 14 from a standard normal distribution, you get values like minus 1.4 pretty much all the time. So that seems reasonable. Then I wrote a little loop that loops through the whole data set to get the predictive z-scores. So again, I set alpha and beta to 0.001, and I set z to be a vector of zeros of length n. And then I loop as I runs from 1 to n. And I use that same exact code I just showed you a minute ago to calculate the predictive z-score for observation I. And there they are. There are the predictive z-scores. They range from, they're obviously sorted from smallest to largest because I started with data sorted from smallest to largest. And they range from minus 1.4 up to plus 3.1. Do any of those numbers seem unusual to you as draws from the standard normal distribution? Well, the 3 is getting a little bit big, right? Of course, that judgment has to be relative to how many observations there are, because if I had 100 observations from the standard normal curve, I would expect a number around 3 to occur. But with only 14 observations from the standard normal curve, 3 is a little bit unusual. I can work out the mean of the z-scores. It does come out satisfyingly close to 0. And I can work out their standard deviation, and it comes out a bit bigger than 1, which is reflective of the fact that that one observation in the right tail that gave rise to the 3.06 z-score was the observation 6 in the data, which is actually looking a little unusual for a Poisson distribution with mean 2.071, for instance. And I can make a little normal QQ plot of these z-scores. The right way to do this actually is not what I just showed you here. This is a very approximate shortcut to what I really should be doing. But like it says here, the figure above is only a crude approximation to the right QQ plot, which would have to be created by simulation. And I'm not even going to spend time saying how to do it correctly, because I'm going to show you a much better way later on. But even so, it's enough already to suggest how the model could be improved. Namely, there is a little hint of extra Poisson variability in this data set. We saw that already at the very beginning. The variance was a little bigger than the mean. And so the VTMR is about 1.15. And so if you wanted to try to improve on this data set, you should probably think about fitting a model that allows for a variance that's bigger than the mean. And in fact, that's exactly what the negative binomial distribution tries to do, or at least this Poisson gamma distribution, which is a generalization of it, does that very nicely, by the way. It sets things up so that the Poisson has the great simplicity, but also the defect that the variance parameter and the mean parameter are the same. And in general, if you were going to try to create a family that was rich on the non-negative integers that allowed for all different sorts of shapes and scales and so on, you'd want one parameter for location and a different parameter for scale, right? So the negative binomial, or at least the Poisson gamma that I've shown you there, does that very nicely. It separates scale from center in a way that allows you to have a lot more flexibility in modeling data that has a form of counts, or at least data that lives on the non-negative integers. In fact, in the same way that earlier today we talked about the mixtures of normals being a model that essentially could get you practically any sampling distribution you want to arbitrary accuracy, you can show that a mixture of Poissons is not enough to get you any possible sampling distribution on the non-negative integers, but a mixture of negative binomials is enough, because it has those two parameters, one for location and one for scale. And so that means that in some sense, that's another way to think about doing modeling without actually having to specify a density. You just think of it as a mixture of negative binomials. Now, it's incumbent upon me, whenever I write down a prior, to see if it has about the right information content, given my actual information base external to the data set, and B, to see if modest and reasonable variations in how I specify that prior tend to lead to more or less the same posterior distribution. That's an important part of Bayesian work. It's called, we would just call it sensitivity analysis with respect to the prior, some phrase like that. There is no unique prior, one and only one prior, that captures the idea of not knowing much external to the present data set when the thing of interest lives somewhere on the positive part of the number line. There's a bunch of different ways to do it, as we've seen. Is it true, even with a sample size 14, that all roads lead to Rome? Or is it true instead that, in fact, small details in how I specify the diffuseness can actually have an uncomfortably large effect on the prior? That's important for me to know, and so I'll do a little study here. So in specifying a diffuse prior for lambda in this case study, several alternatives to epsilon epsilon for the gamma might occur to you. One of them would be, instead of gamma epsilon epsilon, you could try gamma 1 comma epsilon. You could try gamma alpha beta, where beta is small and alpha is some bigger number. And you could try a uniform prior that ranges from 0 to c, like I mentioned before, with some cutoff value c, like 4, that's chosen to be big enough to avoid truncating the likelihood function. So here I've plotted the gamma epsilon epsilon prior again. Now I've plotted the gamma prior with parameters 1 and 0.001 here on the second picture. And in fact, this doesn't look at all like a uniform prior, right? It's not close to flat at all in the region where the likelihood's appreciable. But that's because Maple has done something very literal. It has chosen the vertical scale to emphasize the actual range of the values in the range of the horizontal variable that you're interested in. So it only runs from 0.00996 to 0.001. So when I force it to draw it again, using the same vertical scale I had over here, so this one here had a vertical scale from 0 to 0.05. When I force it to plot again with that vertical scale, it now looks like this. And it is indeed properly extremely flat in the region where the likelihood is appreciable. Now I could try plotting that lambda alpha beta, or rather the prior gamma prior with alpha equals 20 and beta equals 1. You would think this would be a low information content prior because beta is only 1. That's like having one prior vote in the prior data set. But look what it looks like. In the range that's appreciable to us, it looks like that. And in fact, it's not really that close to constant in the region where the likelihood is appreciable. Out there in the right tail of the likelihood, it's starting to give more and more weight to really big values of lambda. And so if I try to use this prior, it's going to actually be a lot more influential than I want it to be because it does not achieve the goal of being relatively close to constant in the region where the likelihood is appreciable. There's still significant likelihood mass out there between 3 and 4, and this prior density is going to way exaggerate those numbers, making the posterior have a posterior mean that shifted sharply to the right, and we didn't want that at all. So this might have seemed like a reasonable thing to do, but it doesn't actually work on this data set. And of course, I can plot, if I plot that same prior across a much broader range of lambda, I do get a prior that's quite diffuse, and it does have only one vote, but the one vote it has is like a data set with a mean of 20. And so when you have 14 votes from the data with a mean of 2 and one vote with a mean of 20, that's going to really grab the posterior mean and shove it pretty far to the right. And so we don't really want that to be happening. So like it says here, gamma 20, 1 does indeed look not far from Gaussian. And at first it may appear that it is indeed relatively flat in the region where the likelihood is appreciable, but we'll actually see that it's quite a bit more informative than we intended. So recalling that the mean and standard deviation of a gamma random quantity are alpha over beta and square root of alpha over beta squared, and that when used as a prior with the Poisson likelihood, the gamma alpha beta distribution acts like a data set with a prior sample size of beta, you could make the following table. So here I've compared 5 different priors in which the alpha ranges from 0.001 up to 20, and the beta ranges from 0.001 up to 1. And then the 5th row is the uniform distribution for any value of C bigger than 4. And I've looked at the prior mean and the prior standard deviation and the posterior mean and the posterior standard deviation. So let's compare these guys. The first row is the prior I used in this case study. The prior mean was 1, the prior standard deviation was 32, and that gave rise to a posterior with a mean of 2.071 and a standard deviation of 0.385. If instead I used the gamma prior with alpha equals 1 and beta equals 0.001, that's like saying that the prior mean is 1,000 and the prior standard deviation is 1,000. So that turns out to be like saying that I think that in the prior that the mean is anything it wants to be between 0 and about 3,000 days. And so that's actually much, much wider than I would regard as reasonable for a description of my real uncertainty about the average length of stay for women who are giving birth to a premature baby. And yet, it turns out not to have that much influence on the posterior mean or posterior standard deviation. It moves them a little bit to the right because now the prior is uniform, it's close to flat, way out into these really, really big regions to the right, none of which we think are appropriate. But it actually hasn't changed things that much. That prior that I tried with alpha 20 and beta 1 turns out to have quite a lot of influence on things because of that picture I showed you. The prior is starting to get really big in the region where the likelihood is just tapering off, and so that really shoves things quite a bit to the right. The posterior mean has moved all the way up to about 3.3, and the posterior standard deviation has gotten a lot bigger. That is not a diffuse prior. And so that one has been a failure from the point of view of what I'm trying to do here. And I could actually even try to resurrected by keeping the alpha 20 and making the beta go to 0.001 so that it looks like it's only getting 0.001 worth of a vote, and the data set's getting a vote, 14 votes. But now this prior has a mean of 20,000 and a standard deviation of 5,000, and so it makes things even worse. The posterior mean is even bigger now, 3.5, and the posterior standard deviation even bigger. So that's what happens when you try to mess around with the alpha in this thing. It's better to keep small values of alpha with this gamma epsilon epsilon prior if you are trying really to create something that is diffuse. And notice what happens when I use the uniform prior. For essentially any value of C bigger than 4, you will get exactly the same results. Compare the posterior mean in SD. Does it look similar to any of the other rows in the data set? It's identical to the results from the choice of alpha equals 1 and beta equals 0.001. It's also identical to Fisher's fiducial idea of just calling the likelihood as a density, just calling that the posterior is like treating the prior as completely uniform. And that turns out in this model to be exactly like what you would get if you used alpha equals 1 and beta equals 0.001. So what's going on here is several things. The gamma 1 comma epsilon prior leads to an analysis that's essentially equivalent to the fiducial approach, which could also be called the integrated likelihood approach, because we're taking the likelihood and thinking of it as like a density and integrating over it instead of maximizing over it. And the uniform 0 C prior for any C bigger than 4 produces similar results. In effect, what you get is the gamma S plus 1 comma N posterior truncated to the right of C, and this truncation has no effect if you choose C big enough, and that's the same posterior that you would have had in Mr. Fisher's fiducial approach. You might say, in effect, that the uniform prior from 0 to C has a prior sample size of 0 in this analysis, and its prior mean, which is C over 2, and prior standard deviation of C over the square root of 12, both of which can be made arbitrarily large just by letting C get really big. Actually, those prior mean and standard deviation numbers are irrelevant because, in effect, the prior sample size is really 0. It's as though there's no information at all coming from the prior, and that's why the likelihood is exactly the same as the posterior, that analysis. So that's just like what Fisher was trying for. And this is an example of how intuition can change, and when you depart from the class of conjugate priors, you might have thought that the prior mean and standard deviation would have had an influence here, but because the sample size is effectively 0, they don't have any effect at all. So the moral is that with only 14 observations, some care is needed through the kind of pre-posterior sensitivity analysis that we just did to achieve a prior that does not affect the posterior very much if that's the correct summary of your information base. And that finishes part 2B of the course. We now have a few more minutes before lunch, so I think I'll go ahead and start right in on part 2C, if that's okay with you guys. And so here we are trying to generalize the story from first case study, arbitrarily long input stream of binary outcomes. So a Bernoulli process that you're prepared to model as exchangeable. Second case study, exchangeable, but now the y sub i's are just living somewhere on the positive integers, and we found that the Poisson was a good place to begin, but it might not be a good place to end. We might need to go farther. Now let's look at what happens when you have a data stream, y1 through yn, that can be modeled as living continuously on the whole real line. There's a wonderful generalization of De Finetti's theorem to continuous outcomes. And I would rather write about it over here on the document camera because the real fancy way to write it is a measure theoretic statement in equation 1, and we don't really need to go there for this course. So let's try to be more pragmatic here. Here is what De Finetti's theorem for continuous quantities says. So you've got the y sub i's, and they all just live on the real line. And you get to see y1 through yn. So you see this part. But if you're prepared and you know that your uncertainty about them is exchangeable, And that would be for the same reasons it was in the Bernoulli case study and in the Poisson case study. If you don't have any covariates, if you don't have any information that helps you to distinguish one unit from another, then your uncertainty is exchangeable. Then, if you're prepared to extend your exchangeability judgment from those finite guys to the countably infinite story that goes like that, like we talked about before, let's think of that as the population, script P, just like we did before, and in effect saying that your exchangeability judgment extends to all the data values in this bigger vector is equivalent to saying that you regard the y1 through yn as like a random sample from that population. If that's true, then you have to start thinking about the cumulative distribution function, capital F, let's call it, of those numbers y1, y2, dot, dot, dot. It acts like the population CDF, in effect. That would be a way to think about what it's doing. So, and it turns out under exchangeability that CDF has to exist. There has to be a limit of this, the cumulative CDF for all the observations you've seen so far, up to observation n, then n plus 1, then n plus 2, out to infinity. That limit has to exist, and it's a good, like a member in good standing of the family of CDFs. And as soon as you know that it exists, what De Finetti says is that this whole story is equivalent to the following two-stage hierarchical story. Namely, if you knew what F was, you'd have to model the yi's given F as IID from F. But then, because F is unknown to you, you have to be prepared to quantify your uncertainty about it external to the data set by putting down a prior. And here I should put in, of course, as usual, the background information. And so this becomes the prior. So this is now De Finetti's theorem for continuous outcomes. And it has considerably raised the bar on what we have to do. Let me remind you what it said last time. When the yi's are binary, it said a model that looked like that, except it said yi given theta were IID from Bernoulli theta. And theta had a prior. That's what the model said before. So look what De Finetti's theorem did for us in the case of binary observables. De Finetti's theorem uniquely specifies the sampling distribution. But now, look what De Finetti's theorem says in the continuous case. The sampling distribution could be anything you could think of in the set of all possible CDFs. We could call script F the set of all possible CDFs on the real number line. And what De Finetti says is that actually, in this prior right here, you have to be prepared to say something about what that CDF looks like external to the data set, with information living only outside the data set. What's that? Oh, I'm sorry. Is it too? If I zoom out, we'll start. Let's see. Yes, I can zoom out. Let's try zooming out. Except zooming out now we end up with not having things cut off. You like that better? You want to zoom in? Okay. Okay, is that better? I thought it was better before, where the page was just as big as the frame. So let's try that. Let's try getting it out to there, where we just start cutting things off. And at that point, that's about the most information I can give you, I think. So look what De Finetti's theorem is saying now. In effect, with the Bernoulli case, the prior was only a prior about that number that represented the success rate in the Bernoulli story, and there was one and only one sampling distribution, namely the Bernoulli story. But now the burden is much bigger on us. We have to be prepared to put a prior on the set of possible CDFs for the data, and that's like saying, it's like putting a prior on the sampling distribution. Check it out, right? Because that's what capital F is. It says if you know what F is, the yi's are IID from F. And so you actually have to be prepared to think about putting a prior on the sampling distribution itself. In other words, in the language we talked about before, This is a very visceral and direct way to talk about model uncertainty. If you're not sure what the right sampling distribution is, then De Finetti is telling you what to do. You have to be prepared to think about what it might be at the time you were designing the experiment before the data has arrived, and put a prior on that set of all possible sampling distributions and then update it given the data. That is the right way to behave in a logically internally consistent manner. Now, why is that harder? Well, what we've done so far wasn't that hard because theta was just a scalar, a single number that lived between 0 and 1, right? So theta just is a number between 0 and 1. How do you start putting priors on entire functions? That's what this says to do. You have to create a distribution whose outcomes, every time you sample from that distribution, each outcome is an entire function that's a cumulative distribution function. Before De Finetti came along with this theorem here, no one had ever thought of that before. We have had, since Bayes in 1760 or so, we've had a fair amount of experience putting priors on numbers and on vectors, and even a little bit of experience in putting priors on matrices. But De Finetti's asking us to do something much more difficult, put a prior on an entire function on it. And so a scalar is just a dimension 1 quantity. A vector is of length k, so that's a k-dimensional quantity. A k by k matrix, it'll often be a covariance matrix, and so it'll be symmetric. It will have roughly k squared entries in it, sort of k squared over 2, something like that. Those are all finite. Here, a function is actually an infinite dimensional quantity, right? Because in principle, if it's a continuous CDF on the real number line, you have to specify its values at an uncountably infinite number of places. And so if you're really going to take this seriously, wow, that's a big upping of the ante. This is the topic of what people call Bayesian nonparametrics, right here. So De Finetti invented, this theorem is from 1937. Without meaning to, De Finetti invented the field of Bayesian nonparametric inference. And it's called Bayesian nonparametrics, BNP for short, because the idea of Bayesian nonparametrics is putting priors on functions. So that's what the phrase Bayesian nonparametrics means, putting priors on functions. And it actually arises in 2 different realms, and then after I finish saying this last sentence, we'll break for lunch. One of them is this realm here, so this is realm number 1. And the other one is in regression settings. So suppose you have a scatter plot where you've measured a variable x and a variable y, and you've got the relationship between them, and it has some weird sort of nonlinear sort of relationship. Then the function that tracks the conditional expectation of y given x might have some strange sort of shape like that in this problem here, for instance. That's another function that you could be uncertain about. And so version 2 of Bayesian nonparametrics is putting priors on regression surfaces, actually putting a prior on where the mean function might be. So this one here is the conditional expectation of y given x, and it's a function. And you're uncertain about it. So why not put a prior on that as well and learn this from the data rather than imposing some structure like, oh, I think it's a quadratic, and so I'll put down a parabola, for instance. If you were doing a better job of really capturing your uncertainty, you would have started out by saying it could be practically anything. The reason I thought it was a quadratic was I looked at the scatter plot, and so start out with it being practically anything. And you see, this is one way to solve the model uncertainty problem, because if we really could do this, then we're making a statement ahead of time about what the possible sampling distributions are without saying that there's only one and only one sampling distribution that we can work with. So if we can really do this, we can solve the model uncertainty problem by, in effect, starting out with a prior that is actually has a lot of it, has its mass spread out very widely in CDF space, so to speak, and yet has the property that when new data accumulates, it moves relentlessly toward what the truth is. And that turns out to be what Bayesian nonparametric analysis does. When you set up the prior correctly, it's very, very diffuse across all possible CDFs, but then once the data starts to arrive, it moves inexorably toward a posterior distribution on what the actual data generating mechanism is. It does the right thing, in other words. But the math is hard, and the computations are hard, and the computations do not scale well. If you have a big data set, Bayesian nonparametrics is hard for you to do using today's algorithms, because the Markov chain Monte Carlo stuff we'll be talking about next time does not scale well to large data sets. So how to do this Bayesian nonparametric stuff with big data sets is an open research problem that people are working on right now, including me. Good, so let's go to lunch. We'll start again at 1:30. And video people, we can shut things off for the next hour roughly and start again right at 1:30. Thanks very much.